Welcome to this explainer. Today, we're diving right into Richard Feynman's foundational lesson that absolutely everything in the universe is made of atoms in perpetual motion. It's one of those concepts that sounds incredibly simple on the surface, but it actually unlocks the most profound mysteries of how our physical world operates. Imagine if some massive cataclysm wiped out all scientific knowledge, and you could pass only one single sentence down to the next generation. What would it be? Well, Feynman believed the atomic hypothesis contains the most crucial information packed into the fewest possible words. The idea that all things are made of atoms, little particles that just keep moving around in perpetual motion. Here's our roadmap for today. We'll start with the ultimate scientific sentence, magnify a drop of water, look at heat, gas, and ice, explore evaporation and dissolving, touch on the chemistry of fire, and wrap up with the incredible leap from atoms to complex life. Let's get into it. All right, Section 1, the ultimate scientific sentence, the atomic hypothesis. This is the core rule that drives literally everything we're going to talk about today. So what actually is the atomic hypothesis? It basically boils down to three core behaviors. Everything is made of atoms. Those atoms never, ever stop moving. And they play this constant game of tug of war. They attract each other from a slight distance, but violently repel if you try to squeeze them too close together. It's a simple idea, but it explains almost everything. And to prove it, let's try a little thought experiment. Moving right along to Section 2, magnifying a drop of water to see the invisible. Picture a single drop of water, just a quarter inch across. If you magnified it 2,000 times with a great microscope, the drop would be the size of a room, and you'd see little paramecia swimming around. But we need to go much deeper. If you magnify that water 1 billion times, we finally reveal the atomic structure. Just to help you wrap your head around that scale, if you blew up a standard apple to the size of the entire Earth, the atoms inside it would be the size of that original apple. When we zoom in that billion times, water is basically just oxygen and hydrogen stuck together. Every oxygen atom has 2 hydrogen atoms holding onto it, forming a water molecule. But don't picture this as a static drawing. It's incredibly dynamic. These molecules are constantly jiggling, twisting, and bouncing. They're stuck together by attraction, sure, but they flow smoothly because they aren't rigidly locked into one unmoving place. Which brings us to Section 3, heat, gas, and solid ice, the states of matter. How do these microscopic, jittery atoms create the completely different states of matter we interact with every single day? Here is the absolute kicker. Heat is literally just motion. That's it. When you feel something hot, you are actually just feeling atoms jiggling really, really fast. The hotter the water, the more violently its atoms are moving. And this one fundamental fact dictates whether a substance is a solid, a liquid, or a gas. Think about what happens when you boil water. In a liquid state, those molecules are packed in tightly, glued together by their mutual attraction. But as you crank up the heat, the jiggling gets so violent that it completely overpowers that attraction. The molecules literally break free and fly apart to become steam vapor, just bouncing around completely independent of one another. So now you've got this gas, like steam or air, and these free-flying atoms are just relentlessly bombarding the walls of their container. That constant chaotic bombardment, that's exactly what creates gas pressure. And here's something fascinating. If you push a piston inward to compress that gas, the atoms bounce off the moving piston with even more speed. They steal energy from the collision. Increased speed means increased jiggling, which means compressing a gas directly makes it hotter. Now let's go the other way. Remove the heat, and those atoms slow down. Eventually, they don't have enough jiggling energy to freely slide past each other anymore. They lock into a rigid crystalline pattern, which we call ice. And the really cool part is that this crystalline structure forms with empty hexagonal spaces or holes in it. That is exactly why ice expands when it freezes. It literally takes up more physical space than chaotic, tightly packed liquid water. Section 4, evaporation and dissolving. These are dynamic processes that we see happening all around us. Let me ask you a highly practical question. We all blow on a bowl of hot soup to cool it down, right? But have you ever wondered what is physically happening at the atomic level when you do that? It feels like magic, but the atomic hypothesis gives us the precise mechanical answer. It's all about evaporation. Every now and then, a water molecule on the surface gets bumped with just a little extra energy, an extra jiggle, allowing it to break free from the liquid. Because it takes that extra heat energy away with it, the water left behind actually cools down. But here's the catch. Molecules in the air are also constantly bouncing back into the soup, returning heat. By blowing on it, you are constantly sweeping away that moist air, preventing those hot molecules from returning and maximizing the cooling effect. Dissolving is this incredibly similar dynamic dance. When you drop a solid salt crystal into water, the water molecules actually orient themselves based on electrical charges. The slightly negative oxygen ends grab onto the positive sodium ions, and the positive hydrogen ends grab the negative chlorine ions. Through pure electrical attraction and constant thermal jiggling, the water literally tears the salt crystal apart, ion by ion. Moving into slightly more explosive territory, Section 5, the chemistry of fire, where atoms change partners. So what exactly is a chemical reaction? Well, melting ice and dissolving salt just move existing molecules around into different arrangements. But a chemical reaction fundamentally breaks apart the atomic partners and snaps them into completely brand new molecular combinations. Take a piece of wood or coal, which is basically a solid chunk of carbon. Oxygen molecules from the air are constantly bombarding it. Now, carbon attracts oxygen way more strongly than oxygen attracts itself. So when they collide, they snap together with absolutely tremendous vengeance. That violent snapping generates a massive amount of motion energy. And macroscopically, we experience that exact burst of kinetic energy as the heat and visible light of a fire. And that brings us to our final chapter, Section 6, From Atoms to Complex Life, the grand finale. Let's zoom out a bit. Compared to a simple process like carbon burning, biology relies on structures that are just unimaginably intricate. Think about the smell of a violet flower. It's not simple at all. It's an enormously complicated, chaotic-looking monster of precisely arranged carbon, hydrogen, and oxygen atoms. It accidentally jostles its way through the air, completely blind, until it lands perfectly inside the exact right receptor in your nose. And we know this for sure. Through some seriously incredible detective work, organic chemists have mapped the exact three-dimensional structure of molecules like alpha iron. That's the molecule responsible for the violet smell. It proves that every unique substance you can see, touch, or smell is nothing more than a specific, measurable atomic arrangement. This leads us to what might be the single most important unifying hypothesis in all of biology. Absolutely everything that living things do, atoms do. There is no magical extra force at play here. Everything is entirely the result of atoms acting according to the exact physics we've been discussing today. I want to leave you with this final, somewhat provocative thought to ponder. If a simple, repetitive pile of atoms can form crashing ocean waves, or rigid ice crystals, or an explosive fire, just imagine the sheer staggering complexity required to create the conscious human being watching this explainer right now. You aren't just a pile of atoms. You are a dynamic, ever-changing, non-repeating masterpiece of atomic motion. Thanks for hanging out with me on this deep dive, and keep questioning the incredible mechanics of the world around you.
Welcome to this explainer. Okay, today we're diving into something absolutely monumental, based on Richard Feynman's legendary lectures on basic physics. Just take a second and think about the sheer complexity of nature. Waves crashing on a beach, the wind blowing, the colors we see, the hardness of rocks beneath our feet, even human thought. It's incredibly overwhelming. Observing nature is kind of like staring at this massive, intricate machine where literally millions of gears are turning all at once, and we're just standing there trying to deduce what drives the whole shebang. While fundamental physics is basically humanity trying to figure out the rules of this ultimate game. By digging into the physical meaning behind all these phenomena, we're going to see how scientists have spent centuries trying to reduce the number of different things in the universe, just to understand how they all fit together.
Real quick, here's our agenda for this incredible journey. 1. The rules of the game. 2. Physics before 1920. 3. The electromagnetic spectrum. 4. The quantum revolution. 5. The subatomic particle zoo. And finally, 6. 4 fundamental interactions. We are going to trace the incredible evolution of physics straight from classical forces right down to the messy subatomic world.
All right, Section 1, the rules of the game. Let's move to and see how this builds, particularly when we try to define what we actually mean when we say we want to understand these rules.
To really explain this, Feynman uses this truly brilliant metaphor. He says we can imagine that all the complicated moving things in the world are part of a great chess game being played by the gods. And us? We are just observers of the game. We don't have the rule book, right? But we are allowed to watch the board. So through observation, reason, and a whole lot of experiments, physicists are just watching the board, trying to catch on to the rules as the pieces move.
Now, what's really interesting about this slide is the clear distinction between knowing the rules of the game and understanding the actual place. Fundamental physics? That's just about finding the basic rules. I mean, even if you know exactly how a bishop moves on a chessboard, it definitely doesn't mean you can instantly understand why a grandmaster moves that piece to a specific square in the middle of a highly complex match. In nature, everyday situations are immensely complicated simply because there are way too many moving parts. Predicting the exact outcome of trillions of interacting atoms? Practically impossible. But if we can deduce the basic underlying rules governing those atoms, well, then we consider that we understand the world.
Okay, let's dive into this. Section 2, Physics Before 1920. We're going to travel back to the classical scientific worldview, just before 1920, when the universe seemed, well, a bit simpler than it does today.
Back then, a major goal for physicists was amalgamation. That's basically taking seemingly different phenomena and realizing, wait a minute, they are actually the exact same thing. For instance, early physicists successfully amalgamated heat and mechanics. They realized that heat is literally just the random mechanical motion of atoms. When an object gets hot, its atoms aren't changing what they are, they're simply jiggling and bouncing around much faster. They also managed to merge electricity, magnetism, and light into one single concept, the electromagnetic field. This is exactly how physics progresses. We keep putting the pieces of the jigsaw puzzle together, reducing the number of different things we have to explain. Now, in this classical view, matter is made of atoms, which are held together by short-range electrical forces. You know the drill. Like charges repel, opposites attract. But let me ask you a question just to illustrate the sheer mind-boggling power of this force. Picture two tiny grains of sand, right? Just a millimeter across, sitting 30 meters apart. What do you think would happen if the positive and negative electrical charges in those two tiny grains of sand weren't perfectly balanced?
If they were entirely unbalanced, like if they only attracted or only repelled without any cancellation at all, they would push or pull each other with a staggering force of 3 million tons. 3 million. The only reason macroscopic objects like us don't violently explode or crush together is because normal matter has perfectly balanced positive and negative charges, constantly canceling each other out perfectly. It's an absolutely mind-blowing realization about the sheer hidden scale of the electrical forces holding ordinary matter together.
And this brilliantly illustrates our next topic, Section 3, the electromagnetic spectrum. Because, as it turns out, these electrical forces aren't just local, static interactions acting between grains of sand. When charges move, they create wave-carrying fields. This is one of the most beautiful unifications in all of nature. If you shake an electric charge back and forth, it sends out waves, and by changing just one single number, the frequency of that oscillation, you get entirely different physical phenomena. Look at this. At 10 to the 6 oscillations per second, you get radio broadcasts. Ramp that up to 10 to the 15th, and suddenly it becomes the visible light we see with our very own eyes. Go even higher to 10 to the 18th, and you get X-rays. Radio waves, visible light, X-rays. They are fundamentally the exact same physical thing, just vibrating at different speeds. How cool is that? Which brings us to Section 4, the quantum revolution. This is where things start to get weird. As physicists kept shaking things faster and zooming in closer and closer to the atomic level, the basic rules of the game fundamentally changed. The comforting logic of the 1920s really began to fracture. So, the crucial point is that Newton's classical laws fail completely on a small scale. In classical physics, you throw a ball, it has a definite location and a definite speed. But in the strange new world of quantum physics, that absolute certainty is entirely replaced by statistical probability. We can only predict the exact odds of finding a particle in a certain spot, never its exact predetermined path. Things on a small scale behave like absolutely nothing we know of in our everyday large-scale world. It's a completely different rulebook. The most famous example of this is the uncertainty principle. This quantum rule dictates that you simply cannot simultaneously know exactly where a particle is and exactly how fast it is moving. Now, this actually solves a massive mystery. Why don't negatively charged electrons just crash straight into the positively charged nucleus? Well, the answer lies in their absolute need for physical room to jiggle. If an electron fell into the nucleus, we'd know its position way too precisely. That would force it to have a massive, highly uncertain momentum, which would immediately shoot it back out again. This required jiggling is exactly why atoms are mostly empty space and why atoms continue to move even when you freeze them down to absolute zero. All this quantum strangeness ultimately led to the formulation of quantum electrodynamics, or QED for short. QED is basically the master theory that brilliantly amalgamates electromagnetism with quantum mechanics, and its predictive power is truly staggering. In principle, QED explains practically all known electrical, mechanical, and chemical laws. The collisions of billiard balls, the glowing color of neon signs, the entirety of chemistry and therefore biology, all of it derives from this one fundamental theory. It is, without a doubt, our greatest success so far in physics.
But the story doesn't end there. Section 5, the subatomic particle zoo. What actually happens when we pry open that heavy nucleus at the very center of the atom? When we look past the electrons and try to examine the actual physical pieces playing the game deep inside?
Well, as experimentalists started smashing particles together, they just kept discovering dozens of new, unconnected, and highly unstable particles hanging loose out of our equations. We have the heavy baryons like protons and neutrons, we have mesons like pions, and we have leptons like the familiar electron and its mysterious, much heavier cousin, the muon. Physicists literally called it a zoo because there were simply too many particles and absolutely no obvious underlying pattern explaining why they all exist. It's like we found this box of random chess pieces, but we don't fully understand their relationships or what nature actually needs them all for.
So, how do we make sense of this chaos? That brings us to Section 6, 4 fundamental interactions. Luckily for us, nature has graciously limited the ways these disparate pieces are allowed to interact with one another. Believe it or not, there are only 4 ways these particles communicate. And notice the staggering difference in strength here. At the top, the strong interaction between mesons and baryons is incredibly powerful, but the underlying law is still largely unknown. Below that is electromagnetism, which, as we just discussed, we understand perfectly through QED. Then comes the weak interaction, responsible for things like radioactive decay, partly understood. And finally, way down at the bottom, practically invisible in its weakness, is gravity. It is 10 to the power of 40 times weaker than the strong force. To put that in perspective, that's a 1 with 40 zeros behind it, just an astronomically tiny fraction.
Which brings us to what Feynman honestly and kinda hilariously called the horrible condition of our physics today. The contrast is just stark. Outside the nucleus, we have a beautiful, perfected amalgamation. We completely understand the mathematical rules governing atoms, light, and chemistry, thanks to QED. But inside the nucleus, we have a messy, chaotic jigsaw puzzle. We are basically groping in the dark. Fundamental physics is still very much an unfinished pursuit, with huge gaps in our understanding of how these strange subatomic pieces actually relate to one another. And that leaves us with this final, truly profound question to consider. As we keep looking deeper and deeper into the universe, finding new rules and smashing together new particles, we have to wonder, are there a finite number of pieces to this puzzle, and will humanity ever finally find the edges of the cosmic chessboard? Thank you so much for exploring the fundamental rules of physics with me in this explainer. Until next time, keep observing the game.
All right, welcome to the explainer. Today, we're diving straight into Chapter 3 of the Feynman lectures. This is basically a masterclass on how physics interconnects with absolutely every other scientific discipline out there. We're going to look at the real physical meaning behind the world around us, and I am incredibly excited to share this with you all. We're going to explore how the microscopic jigglings and wigglings of atoms form the absolute foundation for everything: chemistry, biology, astronomy, and yeah, even psychology. But before we get too deep into the atoms, I want you to consider this quote for a second. The whole universe is in a glass of wine. It's a pretty provocative thought, isn't it? I mean, it sounds like pure poetry. But by the end of this explainer, I promise you're going to see exactly how all the sciences, literally all the secrets of the cosmos, fit seamlessly into a single, simple glass sitting right there on your dinner table. Okay, let's dive into this. Here is our roadmap for today. We'll be covering fundamental science, chemistry, biology, astronomy, geology, and finally, we'll wrap it all up with our universe in a glass.
Starting us off, Section 1, the most fundamental science, the rules of the game.
You know, historically, physics is basically the modern equivalent of natural philosophy. It is literally the foundational bedrock of all our scientific knowledge. Why? Well, because if you want to truly understand any physical phenomenon, you eventually have to ask the big question: where are the atoms and what are they doing? This is exactly why students of biology, chemistry, and geology must eventually study physics. It sets the baseline rules for their entire fields.
Moving right along to Section 2, Chemistry, playing the game.
To really grasp how physics and chemistry relate, think about a game of chess. Physics, specifically quantum mechanics, gives us the underlying rules. It tells us exactly how the pieces are allowed to move. But as we all know, knowing the rules of chess is very different from being a grandmaster who can actually play the game well. In chemistry, predicting precisely what will happen in a complex chemical reaction is incredibly difficult. That's playing the game. But the deepest theoretical explanations for why those reactions happen, they always end up right back at the rules of quantum mechanics. We can actually break this down even further. Early inorganic chemistry mapped out the rules of elements and simple compounds, which really helps substantiate the whole physical theory of atoms. Then we have physical and quantum chemistry. Because chemical reactions involve these massive, chaotic numbers of atoms jiggling and colliding randomly, scientists had to develop an entirely new branch of physics, statistical mechanics, just to track the phenomena of heat and thermodynamics. And finally, organic chemistry. This looks at the exact same atoms, but arranged in the highly, highly complex structures associated with living things. Which brings us to Section 3, Biology, the machinery of life. Now, to tackle the fundamental problems of biology, we absolutely have to look at what's happening chemically inside our cells. And the Krebs cycle brilliantly illustrates this exact cellular machinery. It summarizes just a tiny fraction, maybe like 1%, of the elaborate, non-stop series of reactions occurring inside us right now. Notice how a whole sequence of molecules transforms from one to another in these really small steps. For instance, down near the bottom left, there's the crucial transformation from GDP to GTP, which actually stores up the energy you need for things like muscle contraction. But here is the catch. In a laboratory, pulling off these small chemical steps is actually really tough. Usually, to turn one substance into another, you have to push it over this sort of energy hill called activation energy. If you don't have enough energy, the reaction just won't happen, period. So how does the cell do it? Well, those chemical steps we just talked about are driven by enzymes. Enzymes are these massive protein molecules that act like specialized factory machines. They literally hold the smaller molecules in the absolute perfect position to open a hole, let a new atom in, and completely bypass that energy hill. It's a real game changer. Now, what's really interesting here is asking how the cell actually knows which enzymes to build in the first place, right? The answer is DNA. It's the master blueprint passed from one cell to another. Notice the structure. It's a pair of chains twisted around each other, with a backbone made of sugar and phosphate groups. And right between them, holding the whole shebang together, are specific pairs of crosslinks. Those crosslinks are the secret to how life reproduces physically. Let's just call the 4 types of links A, B, C, and D. The chemistry strictly dictates that A only ever fits with B, and C only ever fits with D. So when it's time to reproduce, the DNA chain literally splits right down the middle. Because an A must pair with a B, the loose materials just floating around in the cell automatically attach to their perfect complements on the split halves. The result? 2 identical, fully formed DNA chains completely ready for a new cell. It is a purely physical chemical mechanism driving the continuation of life. How cool is that? Let's shift gears to Section 4, Astronomy, the stellar furnace. So zooming our scale way out from the microscopic machinery of life to the cosmos. The very beginning of physics actually started with astronomy, just trying to figure out the simple motions of the planets. There's this wonderful anecdote about the physicist who first realized that nuclear reactions must be what makes stars shine. The night after his big discovery, he was out with his girlfriend. She looked up at the sky and said, "Look at how pretty the stars shine." And he replied, "Yes, and right now I am the only man in the world who knows why they shine." She just laughed at him. But honestly, it perfectly captures the immense power of understanding physical laws. Because we understand atoms, we actually know what's happening inside that massive stellar furnace. Step 1, stars are fueled by the intense nuclear burning of hydrogen into helium. Step 2, in the unimaginable heat and pressure at the center of the star, completely new, heavier chemical elements are cooked up. Step 3, the star eventually explodes as a supernova, spitting all those elements out into the void. By analyzing the light frequencies from stars, we've definitively proven they are made of the exact same atoms we have right here on Earth. Literally, this stuff making up your body right now was cooked in a star billions of years ago. Next up, Section 5, Geology and Unsolved Mysteries. Now, lest we get too confident here, there is a lot right in front of us on Earth that we still do not grasp. Take weather, for instance. We know the equations for air, sure, but air is this twisting, swirling, turbulent flow that is incredibly sensitive and unstable, we simply cannot analyze turbulent flow from first principles yet. Or geology. We know earthquakes happen when something snaps, but we don't fully understand the circulating currents inside the Earth that actually do the pushing. Strangely enough, we understand the inside of the sun way better than the inside of our own planet. And psychology? Think about it. If a person learns something, their brain must physically change. But where is a memory stored? What is the actual atomic difference in your nervous system before and after you learn a fact? We literally have no idea. And finally, section 6, the universe in a glass. So the crucial point is this. If you look closely enough at a simple glass of wine, you see the entire universe. You see the physics of the twisting liquid as it evaporates into the air. You see geology right there in the glass itself, distilled from the Earth's rocks. You see astronomy in the very atoms that make up the liquid, all of them originating in the fiery furnace of some ancient star. And you see biology in the complex ferments and enzymes that transformed those grapes into wine in the first place. It is a single, beautifully cohesive physical system. You know, for our own convenience, we tend to divide the world into these neat little boxes: physics, biology, astronomy, geology. But nature makes absolutely no such distinction. The universe is just one beautifully interconnected web of jiggling atoms. So it leaves us with this final, lingering thought. If nature itself makes no distinction between physics, biology, and astronomy, why do our small minds insist on dividing up the universe? Thank you so much for joining me on this explainer today. I really hope it completely changes the way you look at the world around you. Welcome to the Explainer. So today we're diving into Chapter I04, tackling one of the most profound, fundamental rules that governs our entire universe. Now, when you hear the word energy, you probably picture something tangible, right? Maybe a glowing force field from a sci-fi movie, or actual fuel burning in an engine. Well, today, we're going to completely shatter that image. Because energy isn't a physical thing you can just hold in your hand. It is a strictly abstract, perfectly precise mathematical principle. It's essentially a number that, no matter what kind of crazy tricks nature plays on us, always stays exactly the same. Okay, let's look at our roadmap for this explainer. We'll start with the mystery of energy, move on to gravitational potential energy, explore the power of reversibility, check out kinetic energy and motion, look at the many forms of energy, and finally wrap up with the future of energy. Section 1. The mystery of energy, a child's indestructible blocks. To really wrap our heads around how an abstract conservation law works, we kind of need to think like detectives. And honestly, there's no better way to do that than with a classic story about a curious kid and his absolutely indestructible blocks. So imagine a boy, let's call him Dennis the Menace, who has exactly 28 of these indestructible blocks. His mom locks him in a room every day, and every evening she counts the blocks. Day 1, 28 blocks. Phenomenal. But on day 2, she only sees 27. Wait, has the fundamental law of conservation been broken? No, she looks under the rug and boom, there's the missing block. Day 3, there are only 26. She checks the open window and sure enough, 2 blocks were thrown outside. Day 4, she counts 30. But then she remembers his friend Bruce came over earlier and left 2 of his own blocks behind. Even when the blocks are hidden away in a sealed toy box, she can just weigh the box to calculate exactly how many are inside. When the water in the bathtub gets too incredibly dirty to see the blocks, she just measures the rising water level. The whole point here is no matter how complex the room gets, if she accurately accounts for all the hidden variables and anything coming in or out of that room, her mathematical formula always equals 28. Which brings us to this absolutely wild, truly shocking revelation. The brilliant physicist Richard Feynman once said, "It is important to realize that in physics today, we have no knowledge of what energy is." Just think about that for a second. Energy doesn't come in little physical blobs. There are no actual physical blocks to count in the universe. We basically just have a set of mathematical formulas for calculating different numerical quantities. But when we add all those seemingly completely unrelated formulas together, the universe always returns the exact same number. All right, section 2, gravitational potential energy, the law of lifting. Let's ground this in the real world and see how it builds into the physical mechanics we can actually touch and see. To understand energy and mechanics, physicists imagine 2 different types of machines. Irreversible machines are the real-world ones. They have friction, they squeak, they constantly need a little extra push to work. But reversible machines are theoretically ideal. They can lift a weight and then run perfectly backwards to return the universe to its exact original state without losing a single drop of effort. Assuming reversible machines could exist helps us prove a massive fundamental rule. Perpetual motion is physically impossible. You can never ever build a machine that lifts a weight higher than a theoretically perfect reversible machine. Because if you could harvest free power forever, and the universe simply doesn't do free lunches. Take a look at this. It brilliantly illustrates the core concept of gravitational potential energy. Here we have a simple machine balancing 3 units of weight against one single unit. Now, to make it work in the real world, you might have to cheat a bit and pull with a little extra force. But in our perfect, ideal world, how exactly do those distances and weights trade off against each other? Well, if we imagine a perfectly reversible machine, we can figure out the fundamental laws of lifting without even looking inside the gears. Imagine a perfectly spaced rack holding 3 balls and a set of shelves right next to it. By gently rolling the balls onto the shelves, smoothly lowering one ball down, carefully lifting the empty rack, and then rolling them back, we reset the entire machine perfectly. Through pure, beautiful logic, this physical sequence proves that a machine dropping a 1-pound weight a distance of 3 feet will lift a 3-pound weight exactly 1 foot. The math is literally inescapable. Weight times height on one side absolutely must equal weight times height on the other. Moving right along to Section 3, the power of reversibility, one law to rule them all. Once you grasp this simple mathematical balance, it's basically like unlocking a physics superpower. You no longer need to memorize 75 different complicated engineering rules for pulleys, levers, and gears. Take an inclined plane shaped like a 3-4-5 triangle. If you have a 1-pound weight sitting directly on the slant, how heavy does the counterweight hanging straight down need to be to perfectly balance it? Using the conservation of energy, we already know the 1-pound weight moves 5 feet along the slant, but only rises 3 feet vertically. Therefore, the hanging weight must be exactly 3/5 of a pound. No complex vector forces needed. The famous Stevinus's chain proves this beautifully too. Because the heavy bottom loop of the chain hangs completely freely and balances itself out, the weights of the chain resting on the inclines above must also be in perfect harmony, directly proportional to the length of the slant they happen to rest on. And this exact same principle of virtual work scales all the way up to incredibly complex mechanisms. Whether you're using a heavy-duty screw jack to lift a massive 2,000-pound ton of weight, or trying to balance an 8-foot unevenly loaded rod with completely different weights placed at different distances, the exact same underlying law is pulling the strings behind the scenes. Let's actually run the numbers here, because it's pretty wild. For that screw jack, if you turn a 20-inch handle 10 times, the handle travels 1,260 inches just to lift that massive ton a single inch. Because of the conservation of energy, weight times distance remains totally constant. That means you only need a measly 1.6 pounds of force on the handle to lift an entire ton. And for the weighted rod, by just imagining the rod tilting a tiny bit and calculating the height each weight would rise or fall, we can easily calculate that it takes exactly 55 pounds of force to balance the entire system. 0 net change in energy. The ledger always balances perfectly, just like Dennis's indestructible blocks. Section 4. Kinetic energy in motion, the energy of speed. But hey, what happens when things actually start moving? If you drop a weight, it obviously loses its height. So where did the energy go? We know it can't just vanish. Think of a swinging pendulum. You pull it up, release it, and it sweeps down. At the very bottom of its arc, it's completely lost its height. Its gravitational energy has effectively disappeared. But we know for a fact it's going to swing right back up the other side. That's because the gravitational energy didn't vanish at all. It converted entirely into the energy of sheer motion. We call this kinetic energy. And yeah, of course, there's a formula for it. Kinetic energy calculates the exact amount of energy required to lift an object back up to its starting height, based purely on how fast it's moving at the bottom. The universe just effortlessly trades height for speed and speed for height, constantly passing the baton back and forth without ever dropping it. Which leads us to Section 5, the many forms of energy, from jiggling atoms to sheer mass. Because energy is a total chameleon. It doesn't just hide in falling weights and swinging pendulums. It shifts into countless invisible forms all around us. If you stretch a spring, you're storing elastic energy. Batteries hold electrical and chemical energy. Light itself is radiant energy. But here's a truly amazing one. When a bouncing ball finally comes to a dead stop on the floor, where did its kinetic energy go? It turned into heat. And heat is actually just microscopic kinetic energy. It's the internal atoms of the material randomly jiggling and bouncing against each other. The motion didn't stop, it just got way too small for our eyes to see. So the big takeaway here, energy is literally woven into the very fabric of existence. Einstein's famous equation proved that mass itself contains a calculable, absolutely immense amount of energy. Even if an object is sitting perfectly still on your desk, doing absolutely nothing, its sheer physical existence is a massive reservoir of energy, just waiting to be unlocked. Finally, Section 6, the future of energy, harvesting the universe's power. So why does all this abstract math matter to us? Because humanity fundamentally runs on energy. We desperately need fuel. And nature, frankly, is incredibly reckless with it. The sun just dumps massive amounts of radiant energy into empty space, and we only catch a tiny fraction of it. To really understand the scale of the energy we're dealing with, consider this. If we can learn to perfectly control thermonuclear reactions, the hydrogen contained in just 150 gallons of running water a minute would hold enough energy to power the entire United States today. Think about that. A single, small stream of water powering a whole nation. The energy is already there, locked away in the atoms, mathematically and perfectly conserved. The mathematical rules of the universe guarantee that the power exists. The energy always adds up. The only question left is, will our physicists and engineers figure out how to master these universal laws, untangle those incredibly complex equations, and completely liberate humanity from the need for energy? It's an incredibly inspiring frontier, and I'll leave you to ponder that massive future implication. Thanks so much for joining me on this explainer. All right, let's just jump right into it. Welcome to today's explainer. Now, today we're doing something really cool. We are borrowing the absolutely brilliant mind of Richard Feynman to, well, kind of dismantle our everyday assumptions about reality. Specifically, we're digging into chapter I-05 from the legendary Feynman lectures on physics. This chapter is all about the very foundation of our physical universe, how we measure time and distance. We're going to start with the stuff we can easily touch and see, stretch all the way out to the literal edges of the cosmos, and then zoom way, way down into the invisible microscopic world. It's going to be a wild ride. But first, I really want to pose a pretty profound question to you. How exactly do you measure a billion years? Or, say, the distance to a spiral galaxy that's millions of light years away? I mean, we can't exactly unroll a giant cosmic tape measure, right? And we definitely can't check a really old wristwatch. We've got to be clever. We actually have to use the physical laws of the universe as our very own tools. And the truly amazing part about all this, we can do it without getting completely bogged down in impenetrable math. We just need to grasp the deep physical meaning behind the concepts. So here's our roadmap for this explainer. First, the art of observation, then measuring the flow of time, the extremes of time, triangulating the cosmos, probing the microscopic world, and finally, the actual limits of measurement. Okay, moving right along to part 1, the art of observation. So, look, physics isn't just about sitting around thinking deep thoughts, right? It fundamentally depends on real quantitative observation. And to really understand that, we have to look back to a guy many consider the very first actual physicist, Galileo. Before him, people mostly just used philosophical arguments to explain motion. But Galileo, he actually ran experiments. He literally rolled a ball down a wooden trough and measured how far it went in a specific amount of time. Now, the physical difficulty here is massive, mostly because, well, he didn't have a stopwatch. So to mark off equal chunks of time, he used his own pulse. Just imagine that for a second, counting your own heartbeat like 1, 2, 3, and marking the ball's location at each beat. He was literally using his own body as a biological clock to map out physical reality. Talk about hands-on science. In doing that, led him to this beautifully elegant mathematical relationship. If the ball rolls 1 unit of distance in 1 unit of time, it rolls 4 units of distance in 2 units of time, and 9 units in 3 units of time. Distance is proportional to the square of the time. Now, don't let the math scare you. This wasn't just some abstract equation on a chalkboard. This was absolutely groundbreaking. It was the exact moment human beings started mathematically mapping the physical motion of the universe. He turned abstract math into a literal physical tool to predict how reality behaves. Which brings us to part 2, measuring the flow of time. So Galileo used his pulse, sure, but to measure time accurately today, we generally rely on something that happens over and over again in a regular, periodic way. For almost all of human history, that was the Earth's rotation, the day. But here's the catch. When we measure the Earth against the absolute best clocks we can build, we find out our planet is actually kind of sloppy. The length of a day actually varies, and on average, it's slowly down over the centuries. So we had to upgrade. Enter the atomic clock. These babies rely on the internal vibrations of atoms, which are incredibly insensitive to outside temperature or interference. The source text actually points out Professor Norman Ramsey's hydrogen clock, which is accurate to 1 part in 10 to the 9th power. To put that into perspective, that means it wouldn't lose a single second over decades. We've literally swapped out the spinning of our massive globe for the invisible vibration of a single atom, just to keep perfect time. Crazy, right? All right, part 3, the extremes of time. Now, what happens when we need to measure a time span that's, say, millions of years long, or unimaginably tiny, like way shorter than a single second? For deep geological time, we actually have to abandon periodic clocks entirely. Instead, we use radioactivity. We look for a totally different kind of regularity called the half-life. Simply put, this is the time it takes for exactly half of a radioactive sample to decay. So it's not a swinging pendulum ticking back and forth, it's more like a steady, incredibly predictable fading away. And we can actually visually map out that physical meaning right here. See, at time 0, we have our full amount of radioactivity, represented by that 1 on the vertical axis. After one interval of time, that big T on the bottom axis, the radioactivity drops to exactly 1/2. Wait another interval T, and it drops to 1/4. Wait another, it's 1/8. You get the idea. By knowing how much radioactive material was in a piece of wood or a rock when it first formed, and then measuring what's left today, we can literally just trace this curve backwards to find out exactly how long ago it was created. This technique allows us to map the absolute extremes of our universe. Like by looking at uranium slowly turning into lead in ancient rocks, we can measure the age of the Earth at roughly 4.5 billion years. And going the complete opposite way, for incredibly short times, we look at subatomic particles. Take a pi-0 meson. It lives for about 10 to the negative 16 seconds. We don't measure that with a clock. We measure it by seeing the tiny microscopic distance it travels at near light speed before it goes poof and decays. There are even these things called strange resonance particles that exist for only 10 to the negative 24 seconds. Guys, that is a decimal point followed by 23 zeros before you get to the 1. It is literally the time it takes light to cross a single hydrogen nucleus. Just mind-blowing. Let's keep zooming out. Part 4, triangulating the cosmos. Okay, so now that we've totally mastered time, let's step outward into space. How in the world do you measure the distance to something you can never ever physically reach with a meter stick? Well, we use a really clever geometric workaround called triangulation. It's kind of like a completely different definition of distance, totally necessary because space physically forbids us from using standard rulers. It works like this. You establish a known baseline length. You look at your distant object from one end and measure the angle. Then you just walk over to the other end of your baseline and measure the angle again. Boom! Using simple geometry, those two angles and your one baseline give you the exact distance to the object. Let's actually look at this in action. Imagine being one of those early scientists staring up at the night sky, trying to figure out how to track the very first satellite, Sputnik. You'd have two observers at completely different locations on Earth. That right there is your baseline, L. They both measure the angle to Sputnik up in the sky. By calculating where those two invisible lines of sight intersect, scientists determined Sputnik was roughly 500,000 meters high, a perfectly elegant solution. But wait, what if you want to measure the distance to a star? The Earth itself is way too small to use as a baseline. The angles simply wouldn't change enough to measure. So astronomers had to think bigger, a lot bigger. They used the entire orbit of the Earth around the sun. We take a telescope, focus on a star in the summer, and measure the angle. Then, we just wait 6 months until winter, when the Earth has traveled all the way to the complete opposite side of the solar system, and we measure the angle again. Think about that for a second. Our baseline is now hundreds of millions of miles across. This immense cosmic ladder allows us to literally reach out into the void and calculate the distances to our neighboring stars. Moving on to part 5, probing the microscopic world. So from the immense, mind-boggling scale of stars and galaxies, we're going to zoom all the way back down to the microscopic. Now, we can directly see things like viruses using electron microscopes, photographing details all the way down to 10 to the negative 8 meters. We can even figure out the exact spacing of atoms in a crystal by bouncing X-rays off of them. But eventually, we hit a physical wall. See, light and X-rays are waves, and when the thing you're trying to measure is actually smaller than the wavelength itself, the waves just wash right over it. When we get down to the nucleus of an atom, we can no longer see it directly. No way! We have to completely change our tactics to what's called probabilistic measurement. We use particle beam scattering to calculate a nuclear cross-section. Okay, I want you to really try and imagine this. If we shoot high-energy particles into a material, think of them like tiny little bullets being fired into a dense, 1 centimeter block of carbon. Now, there are 100 million atomic layers packed in there. But the nuclei of those atoms are so impossibly tiny, it looks less like a solid wall and more like a really sparse forest. Most of those microscopic bullets are going to pass right through the empty space, but a few of them will hit the trees, the nuclei, and be stopped or deflected. By simply counting how many bullets went in and how many managed to come out the other side, we can calculate the exact fraction that were blocked. And that tells us exactly how much area the nuclei cover, allowing us to calculate their physical size. It's literally like measuring a forest blindfolded just by throwing baseballs into it. And the result of that incredibly clever probabilistic math? We find out that the radius of a nucleus is roughly 10 to the negative 15 meters. That is a millionth of a billionth of a meter. This unit of measurement is so unimaginably small, it actually earned its own name, the Fermi, named after the legendary physicist Enrico Fermi. Which brings us to our final stop, Part 6, the limits of measurement. But listen, there is a serious catch to all of this unbelievable precision. As we try to measure these increasingly tiny scales, we eventually hit a literal brick wall constructed by nature herself. This wall is defined by Heisenberg's quantum uncertainty limits, and this is absolutely crucial to understand. This is not just about our scientific instruments being flawed or not quite good enough yet. No, these are fundamental, unbreakable physical limits built into the very fabric of the universe. It all comes down to the wave nature of matter, because particles also act like blurry, spread-out waves. Trying to pin down their exact location forces their momentum to become totally chaotic. The first rule tells us that the more precisely you measure the position of an object, the less you can possibly know about its momentum. And thanks to relativity, a very similar rule applies to time and energy. If we want to know exactly when a subatomic event happened with perfect precision, we are physically forced to know less about what happened, because the energy involved becomes totally uncertain. Nature is just inherently blurry at that level. We literally physically cannot have a perfectly precise measurement of both. Which leaves us with this final, truly staggering thought drawn directly from Feynman's text. If we push back to the very beginning of the universe, 10 or 12 billion years ago, or if we try to zoom in past the tiny nucleus of an atom into a realm where our very concepts of measurement completely break down, we really have to ask, does an earlier time or a smaller distance even have any physical meaning anymore? It is entirely possible that below a certain scale, our deeply human ideas of space and time just simply cease to exist. Pretty wild, right? Definitely something to ponder as you look up at the stars tonight. Thank you so much for joining me on this explainer, and keep questioning the universe. Welcome to this explainer. When you hear the word probability, you might immediately think of, a dry mathematical convenience. Like it's just a tool we use to figure out poker hands or check tomorrow's weather app. But what if I told you that it's actually the fundamental, awe-inspiring language of the entire physical universe? Today, we're diving into Chapter 6 of the legendary Feynman lectures on physics, and we're going to look at reality completely through the lens of chance. It's kind of the ultimate high-stakes question, isn't it? Can we perfectly predict the future, or does God literally throw dice? We're going on a bit of a journey today. We're going to start with the basic, everyday guesses you might make playing a game in a casino, and we are going to follow that exact same logic all the way down to the fuzzy, incredibly uncertain reality of quantum physics that makes up your very own atoms. So here is our roadmap for today. First, the calculus of guesses. Second, coin tosses and fluctuations. Third, the random walk. Fourth, distributions in physical reality. And finally, the quantum fuzziness. All right, Section 1, the calculus of guesses. Learning how to make better guesses. At its core, probability really just helps us quantify our guesswork. It allows us to speak quantitatively about a situation that is highly variable, but still has some consistent average behavior underneath it all. And the most intuitive everyday example of this is just a simple coin toss. Notice how chaotic raw data actually looks here? If you toss a coin 30 times, you'd expect 15 heads, right? Well, look at this record of 3 actual games of 30 tosses. The first game gave us 11 heads. The second, also 11. The third gave 16. In 3 trials, we didn't get our most likely expected number of 15 even once. So you have to ask, is the coin rigged? Or are expectations just wrong? Well, let's see what happens when we scale this whole thing up. This experiment was expanded to 100 runs, totaling 3,000 tosses. Out of those 3,000 tosses, the total number of heads was exactly 1,493. That is a fraction of 0.498. That's incredibly close to exactly 0.5. So the crucial takeaway here is that while small-scale individual runs fluctuate wildly and totally unpredictably, huge sample sizes actually smooth out those fluctuations, revealing the true underlying probability. Moving on to Section 2, Coin Tosses and Fluctuations, How Order Emerges from Randomness. Let's actually visualize this aggregate data so we can see how that order starts to emerge. Take a look at this graph. Here, we've plotted the results of those 100 games of 30 tosses. The vertical bars show how many times a specific score was reached. Notice how the raw, chaotic coin tosses naturally form this really predictable bell-like shape. A score of 15 heads happened 13 times. The dashed curve there shows the mathematically expected probability. This is known as the Bernoulli or binomial probability distribution. Even though we completely missed 15 in our first 3 tries, this distribution proves that 15 is indeed the single most likely outcome, sitting right there at the peak of the curve. And this brilliantly illustrates the underlying math of those fluctuations. It's almost architectural, isn't it? Look at these branching paths. If you toss a coin 3 times, there's only one way to get all heads, but there are 3 different ways to get 2 heads and 1 tail. As you move from 3 tosses to 6 tosses on the right side, you see the number of ways to reach a certain score building visually. This branching pattern actually forms Pascal's triangle. It's literally the architectural blueprint of probability, showing us exactly why outcomes near the middle, where there are the most paths, bulge up into that bell curve we were just looking at. Okay, Section 3, the random walk, applying this to physical movement. Now, incredibly, atoms and molecules move through space using this exact same chaotic logic. Just imagine a particle taking a step forward or backward completely randomly, exactly like flipping heads or tails. Over a long period of time, its average forward or backward progress is actually 0. But obviously, it does drift away from its starting point. To measure this drift, we use something called the root mean squared distance. Sounds a bit intimidating, but the math is actually beautifully elegant. The typical distance traveled is simply the square root of the number of steps taken. To really see this in action, just follow the jagged progress lines we're charting here. We are tracking a particle taking a random walk of 30 steps. Going up is a step forward, going down is a step backward. Mathematically speaking, a particle taking this squiggly random walk is absolutely identical to nature flipping a coin 30 times. The distance away from the 0 line is literally just the difference between the number of heads and tails. The math of the casino perfectly maps onto the physical movement of particles. Which brings us to Section 4, Distributions in Physical Reality, Seeing Probability in Action. Now, let's scale this up to the continuous physical systems we interact with every single day. Imagine a random walk with varying step lengths, kind of like a gas molecule bouncing around a room. As the number of steps, or in this case, collisions, gets insanely huge, something pretty amazing happens. We get the normal or Gaussian probability density curve. Look at these curves for 10,000 up to 160,000 steps. As time passes and more steps are taken, the curve just spreads out and flattens. And just as we learned a moment ago, that typical spread, the actual width of the curve, grows proportionally to the square root of the number of steps. But what does this curve actually mean for physical reality? Well, because a molecule could have taken a literally infinite combination of random steps, the chance of finding it at one exact, precise, microscopic point is effectively 0. We just can't pinpoint an exact location. Instead, the shaded area under the curve between 2 points gives us the overall probability of finding our particle somewhere within that specific interval. And you know what? We can use this exact same framework for speed. This visually identical curve shows the expected distribution of velocities for molecules in a gas. Think about the room you are sitting in right now. There are roughly 10 to the 22nd power molecules just bouncing around. We obviously can't know their individual speeds, but the shaded area here perfectly describes the expected number of molecules hitting the walls at certain speeds, which is exactly what creates the air pressure you feel around you right now. It's really just probability functioning on a massive scale. And finally, Section 5, the quantum fuzziness, nature's ultimate uncertainty. Up until now, we've treated probability as a really convenient tool for complex stuff like bouncing gas molecules. But at the quantum level, we hit a massive paradigm shift. According to quantum mechanics, probability is not just a tool for what we don't know yet, it is all nature actually allows us to know, period. There is a deeply inherent fuzziness to the universe. If you try to pin down an electron's exact location, you completely lose the ability to know its exact speed. And if you force it to a precise speed, its location just smears out into a blur. You simply cannot know both. It's impossible. Let's see how this builds visually. If we have a curve for position, it has a certain width. Let's call it delta x. We have a similar curve for velocity, delta v. Werner Heisenberg's incredibly famous uncertainty principle basically states that nature demands the multiplied product of those two widths must be at least as big as a fixed constant, specifically Planck's constant over 2m. If you squeeze the width of the position curve to make it super exact, the velocity curve literally must spread out infinitely wide just to compensate. And honestly, this is a deeply unsettling reality. Even history's absolute greatest minds struggled with the universe's inherent fuzziness. Albert Einstein famously rejected this whole idea, stating, "But surely God does not throw dice in determining how electrons should go." He spent years trying to find some sort of hidden mechanism that would remove this uncertainty, totally convinced that there must be a way to know exactly what is going on behind the scenes. But he never succeeded. No one has. This is simply the absolute best description of nature we have. Think about a simple hydrogen atom. It's really not a tiny little solar system with an electron perfectly orbiting a proton. The electron's position is just a probability cloud. The electron is there somewhere, but nature only permits us to know the chance of finding it. So I want to leave you with this final provocative thought. If the very atoms that make up your body are ultimately just mathematical probability clouds governed by the exact same rules as a simple coin toss, how certain can you really be about anything? It's a beautifully complex mathematical uncertainty that makes up our entire world. Thank you so much for joining me on this explainer, and definitely keep questioning the universe around you. Welcome to This Explainer. Today we're unpacking one of the absolute masterpieces in the history of physics, Richard Feynman's Chapter 7 on the theory of gravitation. We're going to go way beyond just memorizing rote formulas here. We really want to grasp the profound elegance and the actual, tangible, physical meaning of gravity. Think of it kind of like a detective story where humanity is slowly piecing together the ultimate rules of the universe. To get there, we've got a great roadmap. We'll start with the geometry of the heavens, move on to the perpetually falling moon, explore tides and cosmic wobbles, see how it's a truly universal force, look at weighing the Earth, and finally, end up at an ultimate unsolved mystery. All right, let's kick things off with Section 1, Geometry of the Heavens and Kepler's Elegance. So, our detective story really begins back in the 16th century. Johannes Kepler was poring over these massive stacks of astronomical tables left behind by Tycho Brahe, and he completely shattered the ancient assumption that planets moved in perfect circles. What he found was that they actually move in precise ellipses, with the sun sitting not exactly in the dead center, but over at one of the focal points. Now, an ellipse isn't just some random oval shape. It's a highly specific mathematical curve, kind of like a foreshortened circle. And that realization completely redefined our map of the solar system. Then comes Kepler's second law, which introduces a really fascinating dynamic. He noticed that planets don't just cruise around the sun at one steady, boring speed. If you draw an imaginary line, a radius vector, from the sun to the planet and track it over, say, a week, it sweeps out a wedge of space. Kepler discovered that these swept-out areas are always exactly equal for the exact same amount of time, no matter where the planet is on its journey. What this means, physically, is absolutely brilliant. A planet's speed isn't uniform at all. The very physics of the orbit demands that the planet accelerates, zooming much faster when it gets close to the sun, and then slowing way down when it's further out. It does all of this purely so that those swept-out areas stay perfectly equal. It's just an incredibly elegant rule of nature. Which brings us to Section 2, the perpetually falling moon and Newton's big leap. Okay, so knowing how planets move is one thing, but figuring out why they move, that's a whole different ballgame. Enter the dynamics of motion. Step 1 is Galileo's principle of inertia, right? Objects naturally want to just coast along in straight lines forever. So for step 2, Isaac Newton reasoned that you don't need, invisible angels pushing planets from behind to keep them going. Instead, to bend that natural straight line into an orbit, you need an inward, sideways force. And step 3, that inward force is gravity. The planets are being continuously pulled directly toward the sun. To really wrap your head around how this creates an orbit, Imagine a physical setup where one ball drops straight down, while another one is fired horizontally at the exact same split second. Because horizontal and vertical motions are totally independent of each other, both of those balls hit the floor at the exact same time. Having horizontal speed doesn't slow down the vertical fall one bit. So let's scale that up. Imagine shooting a bullet incredibly fast. It still falls 16 feet in its first second, just like a rock dropped from your hand. But, and here is the absolute magic of orbits, if you shoot that bullet fast enough, let's say around 5 miles a second, by the time it falls those 16 feet, the spherical Earth has actually curved away exactly 16 feet beneath it. The bullet is perpetually falling, but the ground keeps dropping away at the exact same rate. This is literally what the moon is doing. It's not floating out there, it's falling continuously toward the Earth, but it's moving sideways just fast enough to constantly miss us. Moving on to Section 3. Tides and cosmic wobbles, universal interactions. Now, if gravity is this universal force pulling absolutely everything together, you've got to wonder, why doesn't the Earth just fall straight up into the moon? Well, they balance each other out because they're both falling around a common center of mass. That point is actually located just inside the Earth's crust. So the Earth is effectively swinging around this point in a tiny circle. And because the Earth is pretty rigid but the oceans are fluid, this swinging motion, combined with the moon's uneven pull, causes the water to bulge out. It bulges on the side facing the moon and on the exact opposite side. And there you have it. That's the physical mechanism behind our daily tides. Newton's law of gravitation proved to be an unparalleled master key for physics. I mean, it didn't just explain orbits and tides. It explained why the spinning Earth bulges out at the equator, making it slightly elliptical. It actually helped early astronomers figure out that light doesn't travel instantaneously by measuring delays in the orbits of Jupiter's moons. And perhaps most amazingly, when Uranus seemed to wobble off its expected path, astronomers used Newton's math to predict the exact location of a completely unseen planet that was tugging on it. They pointed their telescopes exactly where the math said to look, and boom, they discovered Neptune.
Next up, Section 4, a truly universal force beyond the solar system.
So, does this exact same mathematical rule hold up out in the deep, unimaginable reaches of the broader universe? The answer is a massive yes. Just look at the orbit of a distant double star system, Sirius A and Sirius B. Even though they're light years away, these massive, blazing suns are locked in a gravitational dance that traces the exact same Newtonian ellipse we see right here in our own solar system. Gravity is, for sure, universally consistent. When Richard Feynman looked at photographs of massive globular star clusters, where hundreds of thousands of stars are held together in a magnificent sphere by this completely invisible tether, he was profoundly moved. He basically said that if you can look at the sweeping structural beauty of a galaxy and not feel the sheer awe of gravitation acting across tens of thousands of light years, well, you'd have to have no soul. Let's look at Section 5, weighing the Earth, the delicate measurement. Okay, so we can see gravity holding entire galaxies together. But could we actually measure the gravitational pull between two normal, everyday objects in a lab? A scientist named Henry Cavendish did exactly that, using an incredibly delicate torsion balance. He suspended two small lead balls on a superfine fiber and then brought two massive lead balls near them. He sealed the whole contraption away from any air currents and just waited to see if the tiny gravitational attraction between those chunks of lead would physically twist the fiber. And incredibly, it did. But Cavendish didn't just prove that small masses attract each other. By measuring the precise amount of that twist, he managed to calculate the universal gravitational constant, which we call G. And here's the real kicker. Once you know G, you can plug it back into Newton's equation to calculate the mass of the giant object pulling on all of us. This experiment literally allowed humanity to weigh the Earth for the very first time. The value Cavendish found for G is a remarkably vanishingly tiny number. And this highlights a really profound truth. Gravity is incredibly weak. Think about it. It takes the entire mass of the planet Earth just to keep your feet on the floor, and it's a pull that you can completely overcome just by jumping into the air. Which brings us to our final act, Section 6, an ultimate unsolved mystery, the machinery of gravity. Because for all of its incredible predictive power, gravity remains deeply, profoundly mysterious. Just consider this dizzying spiral of zeros. If you take two basic electrons, they naturally repel each other electrically, but they attract each other gravitationally. If you compare the strength of those two forces side by side, gravity is weaker by a staggering factor of 1 followed by 42 zeros, 10 to the 42nd power. And right now, modern physics has absolutely no underlying reason for why this fundamental ratio is so gigantically skewed. And this exposes the real heart of the mystery. We possess the math to describe what gravity does with absolute perfection. We can literally drop a rover onto a moving target like Mars using these equations. But physics completely lacks the underlying mechanism to explain how it does it. There are no gears, there are no strings, no colliding particles to explain how the sun reaches across 93 million miles of completely empty vacuum to grab onto the Earth. Even Newton himself refused to guess. He basically said, "I'm just giving you the math." So we're left to ask the ultimate Socratic question of physics. What is the actual machinery of gravity? What physically makes it go? Centuries later, Albert Einstein stepped in with relativity, brilliantly describing gravity not as some invisible string, but as the actual warping and curving of the fabric of space-time itself. But we still hit a wall. When we try to look at the universe at the smallest quantum scale, gravity simply refuses to fit in with the other fundamental forces. Finding a unified quantum theory of gravity remains the absolute holy grail of modern physics. So I'll leave you with this to ponder. If gravity shapes everything from the tides in our oceans to the swirling of supermassive galaxies, yet remains totally unexplained at a quantum level, what deep underlying secret of nature is gravity still hiding from us?
Okay, let's jump right into this explainer. Today we're going to discover how trying to describe something as simple as the everyday motion of objects actually forced humanity to invent an entirely new branch of mathematics. We're pulling our focus directly from the brilliant mind of physicist Richard Feynman, specifically looking at the physical meaning of motion as he laid it out in Chapter 8 of his famous lectures. You know, we all think we inherently understand what it means for something to move, right? But as you'll see, pinning down exactly how things move requires some pretty profound leaps in logic.
To really grasp the deep physical mystery we're unpacking today, I want you to consider this classic joke. So, a speeding lady gets pulled over by a police officer. The cop walks up and says, "Lady, you were going 60 miles an hour." And she looks at him, totally confused, and replies, "That's impossible, sir. I was traveling for only 7 minutes. How can I go 60 miles an hour when I wasn't going an hour?" Now, if you're the cop, you're probably just going to write the ticket. But if we want to be intellectually honest here, how do we answer her? What does it actually mean to have a specific speed at a single, frozen moment in time?
So here's how we're going to break this all down. We'll start with describing motion intuitively, look at the paradox of speed, dive into calculus by slicing time, reverse the math with integrals, explore acceleration and forces, and finally, look at motion in the real world.
All right, let's kick things off with Part 1, describing motion intuitively.
We're going to begin with literally the absolute simplest physical change we can observe, an object's position changing over time. And before we get into complex three-dimensional space, let's just stick to a single dimension. Think of a car driving down a straight road. Now, if you map out that car's journey, the distance over time, the path is going to look incredibly jagged and complex. The car starts, it accelerates, maybe it stops at a red light around minute 4, speeds up again, and then, gets pulled over by a cop at minute 9. It's messy. But compare that to a falling ball. Its path traces a perfectly smooth, completely predictable parabolic curve. It turns out that a falling body moves in a much simpler, far more fundamental mathematical way than a car in traffic ever could. And if you look really closely at the actual data for that falling ball, we start to see a beautifully clean mathematical relationship. At 1 second, it falls 16 feet. At 2 seconds, it's at 64 feet. At 3 seconds, 144 feet. There's a pattern here. The formula for this curve is simply that distance equals 16 times the time squared. Because we have this precise, elegant mathematical formula, we can pinpoint the ball's exact location at literally any fraction of a second, which is something we absolutely could not do with that messy, incomplete data from the car. Moving right along to Part 2, the paradox of speed. So, this brings us right back to the speeding lady and the cop, and the inherent mind-bending difficulty of defining what speed actually is. Even the ancient Greeks, as brilliant as they were terribly confused by this exact problem. Think about it. If the ball is constantly accelerating, meaning it's falling faster and faster every single fraction of a second, how on earth do we find its exact speed at precisely the 5-second mark? Sure, we know it fell a certain total distance during that 5th second, but that only gives us an average speed for the whole second. And because gravity never takes a break, the ball is going faster at the end of that second than at the beginning. We don't want an average.
We want to know exactly how fast it was moving at that single frozen instant of 5 seconds. Which brings us to part 3, calculus, slicing time.
To solve this paradox, brilliant minds like Isaac Newton and Gottfried Wilhelm Leibniz realized they had to play a sort of conceptual trick with time itself, and in doing so, they invented differential calculus. Here's how the trick works. To find the exact speed at exactly 5 seconds, we don't look at a whole hour or even a whole second. We look at an infinitesimally short slice of time. We check where the ball is at 5 seconds and then where it is at 5 plus just a tiny extra bit of time, let's say 1,000th of a second. We find the tiny extra distance it traveled in that tiny extra time, and we divide that distance by the time. By taking an infinitesimal distance and an infinitesimal time and shrinking that time slice smaller and smaller, we get closer and closer to the true instantaneous speed.
So the absolutely crucial takeaway here is that velocity is defined mathematically as the limit of the distance traveled divided by the time required, as that time interval gets vanishingly small. In physicist notation, we call that tiny slice of distance delta S and that tiny slice of time delta T. We just sit back and watch what happens to that ratio as delta T shrinks right down towards 0.
This whole process of finding the exact instantaneous rate of change, that is called finding the derivative. When we take the formula for our falling ball's distance, which remember was 16 times t squared, and we apply this mathematical process, we find that its derivative, its velocity, is exactly 32 times t. So, at exactly 5 seconds, you multiply 32 by 5 and you find the ball is moving at precisely 160 feet per second. Boom! We have just solved the cop's problem. The lady was traveling at a rate that, if maintained, would absolutely cover 60 miles in an hour, measured in an infinitesimal slice of a second.
Okay, part 4, reversing the math with integrals. Let's tackle the next logical question. If we can find the exact speed by taking the derivative of the changing distance, can we run the whole process in reverse? Say we only have the falling ball's velocity at different times. It starts at 0, hits 32 feet per second after 1 second, 64 after 2, and so on. To find the total distance from just the speed, we express the distance in terms of infinitesimals again. We take the speed at a given instant, multiply it by a tiny sliver of time to get a tiny sliver of distance, and then we just add all those tiny slivers of distance up.
We call this process of adding all these tiny pieces together integration. Mathematicians actually use a symbol that looks like a great stretched out S, standing for sum, to represent this. Integration perfectly undoes the derivative. Just as velocity is the derivative of distance, distance is the integral of velocity. The two concepts just lock together perfectly, like pieces of a puzzle.
Next up, part 5, acceleration and forces. Now we're going to introduce a brand new level of complexity. We know how distance changes to give us velocity, but how fast is the velocity itself changing? Well, just as velocity is the derivative of distance, acceleration is the derivative of velocity. It's the exact same mathematical tool, just applied one layer deeper. It tells us how many feet per second the speed changes every single second. It is literally the rate of change of the rate of change.
For our falling ball, we know its velocity is 32 times t. If we take the derivative of that, we just get 32. What this means is the constant acceleration is 32 feet per second per second. The velocity increases by an additional 32 feet per second every single second that ticks by. And why is it constant? Well, as Newton's laws tell us, the physical force of Earth's gravity acting upon the ball is constant. The math is just perfectly reflecting the physical force.
And finally, part 6, motion in the real world. Let's take these one-dimensional concepts out of the abstract and drop them into the three-dimensional reality that we actually live in. Because, let's face it, we don't just move in straight lines. If a particle moves in a plane, we just establish an x-axis and a y-axis. And the beautiful part here is that we can treat the horizontal motion and the vertical motion as two completely independent things. We find the x velocity by taking the derivative of the x distance and the y velocity by taking the derivative of the y distance. To find the actual total velocity, we just use a bit of geometry, specifically the Pythagorean theorem, to combine those two components. Let's look at how this builds a real-world path. Imagine shooting a ball perfectly horizontally. It moves horizontally with a constant velocity, right? So distance x equals velocity times time. But simultaneously, it's falling vertically with constant acceleration due to gravity, meaning distance y equals -1/2 gravity times time squared. When you combine these two independent motions and eliminate the time variable, the math flawlessly draws a curve. And that curve is a parabola,
It exactly mirrors how physical objects, from thrown baseballs to jets of water, behave in actual reality.
It leaves us with a truly profound realization. By simply trying to accurately describe how a lady gets a speeding ticket or how a ball drops from your hand, we literally had to invent the mathematics of the infinitesimal. And once we map those infinitesimals onto the real world using axes and geometry, we find something incredible. The mathematical tools invented to figure out a speeding ticket are the exact same tools that unlock the mechanical secrets of the cosmos. Everything from a falling apple to a comet in orbit obeys these elegant rules of change. Thanks so much for joining us for this explainer, and keep questioning the mechanics of the world around you.
Welcome to this explainer. Before Isaac Newton came along, the way planets moved was just a massive, profound mystery. Sure, Galileo had made a huge advance by discovering the principle of inertia, the idea that an undisturbed object just keeps moving in a straight line, but Galileo couldn't explain how an object actually changes its speed or direction when something affects it. Newton provided that missing piece. Today, we're unpacking the actual physical machinery of dynamics. We are going to see exactly how Newton's insights allow us to predict everything from the simple bouncing of a desk spring to the incredibly complex orbits of the planets.
Here is our roadmap for today. We'll start with the mystery of motion, unpack speed and velocity, look at forces in the real world, solve motion step by step, and finally, predict planetary orbits. Let's get right into it.
Part 1. The Mystery of Motion.
So before Newton, planetary motion was essentially this beautiful, completely inexplicable clockwork. Newton changed the game by zeroing in on one specific thing: momentum. Now, we toss the word momentum around all the time, right? Like saying a sports team really has momentum going into the second half. But in physics, words have surgically precise meanings. Momentum is exactly an object's mass, which is just its inertia, how stubborn it is to get moving, multiplied by its velocity. Mass times velocity. It's a simple combo, but understanding it perfectly sets the stage for Newton's big reveal. And here is that reveal, his second law stated plainly. The time rate of change of a quantity called momentum is proportional to the force. Okay, what does that actually mean for us? The absolutely crucial takeaway is that a force doesn't just shove things around randomly. It specifically changes an object's momentum over a period of time. And assuming our object isn't mysteriously gaining or losing mass, this means the force is directly changing the object's velocity. It's causing acceleration.
Which brings us to Section 2, Unpacking Speed and Velocity.
To really track these changes in momentum, we absolutely have to draw a hard line between two concepts we usually treat as the exact same thing: speed and velocity. Speed is just the magnitude. It's how fast you're going, say 60 miles per hour. End of story. But velocity is magnitude and direction. It's 60 miles per hour, heading precisely north-northeast. And in physics, we care deeply about that exact direction because forces push in exact directions. So a change in velocity doesn't just mean speeding up or hitting the brakes, it can also mean taking a corner at the exact same speed. Mind-blowing, right?
Think about a single diagonal movement in 3D space. It looks like one motion, but it's actually made up of three simultaneous, completely independent changes along the x, y, and z axes. We can completely nail down a velocity by breaking it into how fast the object is moving horizontally, how fast vertically, and how fast in depth. It's like a 3D grid. So when a force acts on an object, it causes an acceleration, which, remember, is literally just a change in velocity. The velocity shifts to a new direction and a new magnitude. But honestly, we don't have to panic at how complex that diagonal shift looks. We just look at the changes in the x, y, and z components independently. It's brilliant. It effectively splits Newton's second law into three separate, super manageable laws. The force in the x direction changes the velocity in the x direction, and so on. Divide and conquer.
Moving on to Section 3, Forces in the Real World.
Let's bring this into a physical sandbox. Picture a mass hanging on a spring. Well, ignore gravity for a second and just look at the force of the spring itself. This setup is beautifully simple. The force the spring exerts is exactly proportional and perfectly opposite to how far the mass is pulled or pushed away from its resting point. You pull it down, it pulls up. Push it up, it pulls down. The further you stretch it, the harder it fights back. Let it go, and we all know it bounces up and down, oscillating. But the real question is, can we mathematically predict that exact continuous curve?
That brings us to Section 4, Solving Motion Step by Step.
You might be thinking we need some highly advanced, headache-inducing calculus to solve a system where the force, acceleration, velocity, and position are literally changing every single millisecond. But we don't. We can just use what I like to call the next instant loop. It is elegantly simple. Step 1, we start with exactly where the object is right now and how fast it's moving. Step 2, because we know its position, we know the force the spring is exerting, which immediately gives us the acceleration. Step 3, we apply that acceleration over a tiny fraction of a second to find its new velocity. Step 4, we use that new velocity to predict its new position a fraction of a second later. And then, we just repeat the whole shebang. Let's actually run this loop every 0.1 seconds and build out a data table. At time 0, it starts from rest at position 1. Because it's stretched out, it has a strong negative acceleration, it is being yanked downward. Fast forward just 0.1 seconds, it's gained some negative velocity, and its position has dropped slightly to 0.995. And here's the kicker. Because its position changed, the acceleration changes too. We're doing dynamic calculus here, folks, but with nothing more than basic addition and multiplication.
If we keep cranking out those rows and plot those simple step-by-step arithmetic dots, look at what we get. We reveal this perfectly smooth curve. It matches the exact, continuous mathematical solution of an oscillating spring perfectly. Simply by slicing time into tiny chunks and updating the forces, we've entirely decoded the motion.
And finally, Section 5, Predicting Planetary Orbits. All right, here's where it gets really fun. We are going to take the exact same step-by-step mathematical machinery we just used for a bouncing desk spring and scale it up to a massive cosmic level. Instead of a spring pulling a mass to the center, we have the sun's gravity pulling a planet inward. And just like we saw earlier, we don't need to tackle that diagonal force head-on. We can slice this gravitational pull into a horizontal x component and a vertical y component, just using simple similar triangles based on where the planet is right now. So check out our planetary loop. It is identical to the spring. We start with the planet's current cosmic coordinates and its velocity. We calculate its radial distance to the sun to figure out the exact strength of gravity at that exact spot in space. Then we split that into x and y accelerations. We use those to compute the planet's new velocity for the very next instant. And we use that to lock in its new position. Boom. Then we loop it again. If you chase a planet through roughly 20 steps of these calculations, mapping its x and y coordinates at each tenth of a unit of time, this absolutely beautiful curve begins to emerge from the dots. At the start, the planet is moving rapidly, and as it swings higher away from the sun, it slows down, carving out a flawless orbital path. We are mathematically predicting celestial motion using literally nothing but current positions and the persistent pull of a force. No magic, just math. Now, doing this by hand for one planet with a few steps? Super tedious, but computing machines totally change the game. Even the early basic computers described in our source material could crank out 3,000 of these computational cycles per second. By shrinking that time step to an incredibly tiny fraction of a second, we can track Jupiter or Uranus, accounting for the complex gravitational pulls of all the other planets at the exact same time, and map out years of flawless orbital data in mere minutes. To quote the text directly here, armed with the tremendous power of Newton's laws, we can calculate even the tremendously complex motions of the planets. Just take a second to appreciate that arc. We started this explainer looking at a simple bouncing spring, and simply by breaking motion down into isolated x, y, and z forces over tiny slices of time, we've gained the power to predict the intricate, billion-year dance of the entire solar system. It's a real game changer. Which leaves us with a rather profound, kind of mind-bending thought. If this step-by-step machinery is universally true, if the next instant is always mathematically determined by the current position, the current velocity, and the present forces, if we had a computer large enough to know the exact starting positions and all the forces at play for every single particle, is the future of the entire physical universe completely predictable? It's a fascinating question to ponder as you go about your day. Thanks for joining me for this explainer, and keep questioning the mechanics of everything around you.
Welcome back to the explainer. So, imagine trying to physically stop a heavily loaded shopping cart rolling down a hill, and then compare that to stopping a completely empty one. Even if they're moving at the exact same speed, your muscles instantly feel a profound difference in reality, right? Well, that visceral physical feeling is our entry point to May. We're exploring one of the most elegant and universally binding rules of our universe, the conservation of momentum. But we aren't just going to sit here and memorize textbook formulas. We're going to build this concept from the ground up, relying on the brilliant first principles approach of legendary physicist Richard Feynman. We'll strip away the complex math and use pure physical logic to understand exactly how and why things move the way they do. Okay, here's the roadmap for our explainer today. We'll start with universal principles, then move into action and reaction, the relativity cheat code, an air trough lab, elastic versus inelastic collisions, and finally, we'll look at the extremes. All right, Section 1, Universal Principles, Beyond Brute Force Math. You know, we often think of physics as just, well, plugging numbers into a computer to calculate exactly where an object's going to be. Like if you drop a ball or track a single planet orbiting a star, you can use simple equations to find the exact path. You can even use heavy numerical methods for slightly more complex stuff. But what happens when two cars crash? Or when you try to track the motion of, say, 100 million billion gas molecules in a tiny cubic millimeter of air? Brute force math completely breaks down. There are just way too many vectors, too many invisible collisions happening billions of times a second. It's literally physically impossible to calculate every single variable. And that chaos, that's exactly why we desperately need overarching universal principles, rules that hold absolutely true no matter how incomprehensibly complex the system gets. Which brings us to Section 2, Action and Reaction, Newton's Insight. To find our universal rule for momentum, we really have to start with the one foundational truth Isaac Newton gave us about the nature of forces. Action equals reaction. Let's make this beautifully physical. Imagine you and a friend are both sitting in rolling office chairs, facing each other. If you reach out and push your friend's chair, you don't just stay still while they roll away, do you? No, you violently roll backward too. The force pushing them away is perfectly matched by an equal and opposite force pushing you back. The incredible implication here is that if we look at the entire system, you and your friend together, the internal pushes and pulls perfectly canceled each other out. The system as a whole didn't gain any overall movement in one unified direction. Basically, internal forces can never ever change the total motion of an isolated group. So we can translate that profound physical truth into a simple mathematical master number. If you take every object's mass, multiply it by its velocity, meaning its speed and direction, and add all those pieces up, you get a number that is firmly locked in by the universe. This sum is the total momentum, and whether the objects are gently bumping like billiard balls or violently exploding into 1,000 pieces, as long as no outside forces interfere, this master number beautifully, flawlessly never changes. Moving on to Section 3, Relativity Cheat Code, Symmetrical Logic. Now, Richard Feynman absolutely loved to find ways to prove things without getting bogged down in equations. And to do this, we need a mental shortcut. Enter Galilean relativity. The definition here is key. The laws of physics look exactly the same whether you're standing still or moving with a uniform speed in a straight line. Just imagine you're in an airplane, cruising perfectly smoothly at 500 miles per hour. If the windows of that plane were painted completely black, you'd literally have no physical experiment you could perform inside that cabin that would tell you if you were moving or just parked safely on the runway. If you bounce a ball, it goes straight down and straight up. The universe simply doesn't care about uniform speed. So let's use that. If we detonate a tiny charge between two identical blocks, nature has no built-in preference for left or right. So logically, those blocks just have to fly apart at the exact same speed. Conversely, if two identical blocks are flying toward each other at the exact same speed, when they collide and stick together, they must stop dead. There's no physical reason for the newly stuck-together clump to drift arbitrarily to the left or to the right. Perfect symmetry is our baseline truth. Section 4, Air Trough Lab, the visual proof. Symmetrical logic is great in our heads, right? But to actually prove it, Feynman described an ingenious apparatus to visualize these invisible laws in reality. To completely kill friction, that annoying force that constantly ruined Galileo's ancient sliding experiments, we use an air trough. Basically, compressed air is actively pumped through tiny holes along a track, creating a perfect cushion that specialized metal gliders literally float on. These gliders are equipped with delicate spring bumpers and a tiny cylinder right in the middle, loaded with a pristine explosive charge that's triggered by an electric spark. It is pretty much the ultimate testing environment. So let's test our symmetry logic. We start two equal floating masses touching at the center and trigger the spark. Pop! Just as predicted, they shoot outward at exactly equal and opposite speeds. They travel the exact same distance, hit the spring bumpers at the ends of the track at the exact same fraction of a second, perfectly reverse direction, and slide back to kiss gently in the dead center. The total momentum of the system started at an unbothered zero, and even after a violent explosion, it remains exactly zero.
Okay, now let's try something much harder. What happens if one mass is moving at velocity v and hits an identical mass that's standing entirely still, and they stick together? To solve this without using tricky math, we use our Galilean relativity cheat code. If we imagine driving alongside this track in a car at a velocity of -v, the physics must remain identical. From the car's rolling perspective, the originally moving block now looks like it's standing perfectly still, and the stationary block looks like it's rushing toward us at twice the speed. When we step out of that imaginary moving car and stand still, the math reveals a beautiful truth. If a mass moving at a certain velocity hits an equal stationary mass, and they permanently stick, the new combined mass, which is of course now exactly twice as heavy, moves at exactly half the velocity. The math perfectly balances. Doubling the mass means having the velocity to keep the master number constant. Momentum is fiercely conserved.
And we can apply this exact same logic to uneven masses too. If a single moving mass hits a stationary mass that's twice its size, and they stick together, they become a heavy new clump that's 3 times the original mass. And because that total momentum master number simply cannot change, that heavy new clump must slowly drift away at exactly 1/3 the original speed. This is incredibly powerful, you guys, because it lets scientists completely bypass the chaotic, messy, crushing phase of an impact entirely. We don't need to know how the metal crumpled. We just use momentum to immediately know the final drifting state.
Section 5, elastic versus inelastic. Where does energy go? At this point, we really must distinguish between two fundamental types of collisions, inelastic and elastic. An inelastic collision is when objects hit and stick, kind of like throwing two balls of soft putty at each other. In these sticky collisions, momentum is perfectly conserved, but kinetic energy, the actual energy of motion, appears to be lost. But it doesn't just vanish. It gets transformed into internal heat. It becomes the invisible, microscopic jiggling of the atoms inside the putty. An elastic collision, however, is entirely different. Imagine perfectly rigid steel balls bouncing off one another. They compress briefly, storing energy like a tight spring, and then snap forcefully back apart. In a perfectly elastic collision, both momentum and kinetic energy are fully conserved. Now, in our messy, everyday macroscopic world, perfectly elastic collisions don't really exist. A little energy is always lost to heat or like a loud sound. But at the microscopic level, it's a completely different story. The collisions between elementary gas molecules are practically perfectly elastic. Why? Because atoms simply don't have internal gears, wheels, or springs to absorb that energy. When they violently crash into each other, they have absolutely no choice but to bounce off with their kinetic energy fully intact.
Finally, Section 6, the extremes, rockets, relativity, and quantum.
For a law to truly be universal, it has to survive the absolute extremes of our universe. So let's look at the cosmos. First up, rocket propulsion. A rocket moves in the dead vacuum of space not by pushing against air, but by ejecting a tiny mass of exhaust backward at a terrifying velocity. To conserve momentum, the massive rocket must violently recoil forward. Second, electromagnetism. Light itself, despite having zero mass, actually carries momentum. When light bombards an object, it exerts a tiny measurable physical pressure, literally enough to push massive solar sails through deep space. And even in the bizarre, unpredictable world of quantum mechanics, where particles act like smeared-out waves, the conservation of momentum miraculously survives.
Now, Albert Einstein did realize he had to tweak this law for things moving dangerously close to the speed of light. Einstein discovered that as an object gets incredibly fast, its actual mass physically increases. Because the mass scales up, the momentum scales up too. But the profound beauty is, once you account for this relativistic mass, the total momentum before and after a high-speed collision is still perfectly conserved. The classical formula bends, for sure, but the core conservation principle remains the untouchable anchor of reality. Richard Feynman summed this up perfectly, noting that while energy can easily hide as microscopic heat or internal vibration, momentum, as a mechanical quantity, is difficult to hide. Because momentum is strictly directional, if an entire object is drifting to the right, that momentum is obvious, measurable, and completely impossible to conceal. It can't just retreat into the microscopic jiggling of atoms. It has to go somewhere. So,
We traveled from simple sliding blocks on an air trough to the incredible speeds of light and the realms of quantum waves, all tied together by one absolutely unbreakable physical rule. So I'll leave you with this to ponder. If the conservation of momentum dictates everything from the recoil of a massive spacecraft to the literal light bombarding our planet, what other invisible, perfect symmetries are quietly shaping your physical world right now without you even noticing? Thanks so much for joining me on this explainer, and keep looking for the hidden rules of the universe. Hey everyone, welcome to this explainer. I am absolutely thrilled you're tuning in because today we are going to look at the universe through an entirely new lens. You see, grasping physics isn't just about memorizing dry formulas or calculating exactly where a thrown ball is going to land. It's really about understanding the beautiful, profound symmetry of the universe itself. We're going to explore how nature's rules stay incredibly consistent no matter how we look at them, and how physicists invented a downright brilliant mathematical language to capture that consistency. So let's kick things off with a really massive question. Where exactly is the center of the universe? I mean, if we want to measure where things are and how they move, where is the ultimate point zero? Suppose we build a complex, completely identical machine in two entirely different locations. Will they obey the exact same physical laws? Well, if we have to factor in their location just to figure out how they operate, then there's no real underlying order to the universe. But if those machines operate in perfect parallel, if the laws of physics genuinely don't care where in the universe you place them, then we say those laws possess symmetry. To really pin this concept down, we should look at how the brilliant physicist Hermann Weyl defined it. He said, "A thing is symmetrical if one can subject it to a certain operation and it appears exactly the same after the operation." Think of a perfectly smooth, round vase. If you rotate it 180 degrees, it looks exactly the same, right? This philosophical idea of symmetry isn't just some abstract thought experiment, it's literally the absolute foundation of all mechanics. If we operate on our physical laws by moving our perspective to a totally new place, those laws should still appear exactly the same. Okay, here's our roadmap for today. First, symmetry in physical laws. Second, moving and rotating axes. Third, defining the vector. Fourth, the rules of vector algebra. Fifth, acceleration on a curve. And finally, number 6, the scalar dot product. All right, let's dive into part 1, moving and rotating axes. To actually measure the physical world, to calculate position or velocity or force, we need a coordinate system, an x, y, and z axis. But what happens when two different people pick completely different starting points? Think about two observers. Let's call them Joe and Mo. They both have parallel coordinate systems, but Mo has shifted his origin over by a specific distance. Let's call it A. Because of this shift, when they measure the exact same point in space, their position measurements are going to differ. Mo's x position is just equal to Joe's x minus A. But what about the actual physical forces pushing on an object at that point? Well, because they are just viewing the system from different parallel spots, the force calculated along Mo's axis is completely, perfectly identical to the force along Joe's. They measured different physical coordinates, sure, but the physical reality remains completely symmetrical. But what if Mo doesn't just slide his axis over? What if he tilts the whole thing entirely? Imagine Mo's axes are now rotated relative to Joe's by a certain angle, theta. If Mo measures a point in space now, we actually have to use trigonometry, specifically sine and cosine, to translate his rotated perspective back onto Joe's standard grid. Mo's new x-coordinate is essentially made up of a piece of Joe's x and a piece of Joe's y. Now here is where it gets really interesting. Think about what happens when we calculate a physical force in this rotated system. The mathematical formulas for the forces transform identically to the physical coordinates. The equation for the new force components uses the exact same sine and cosine mixing as the physical spatial coordinates did. This is kind of a mathematical miracle, honestly. It proves that Newton's laws hold completely true no matter how you turn or tilt your axes. Part 2. Defining the vector. Doing all that tedious trigonometric translation every single time you change your viewpoint? Yeah, that's exhausting. So physicists invented a brilliant mathematical shortcut, the vector. Now, you might have heard a vector described simply as an arrow with direction and magnitude, but in physics, it is so much deeper than that. A vector is any physical quantity associated with 3 numbers that transform exactly like the components of a step in space when your coordinate axes change. It's this incredibly robust tool that inherently guarantees physical relationships stay unchanged. They remain completely symmetrical even as we rotate our perspective. Force is a vector, for example, simply because it transforms exactly like a physical step in space does. Part 3. The rules of vector algebra. Now that we actually have these powerful vectors in our toolbox, how do we combine them mathematically? First up, addition. How do you add two arrows pointing in totally different directions? Well, geometrically, adding vector A to vector B just means taking the tail of vector B and fitting it directly onto the head of vector A. The total sum, which we can call vector C, is just the new arrow drawn from the very beginning of A to the very end of B. The beautiful thing is, you don't even need coordinate axes to do this. It is a pure geometric reality. And you know what? Vector subtraction is honestly even easier. If you want to find vector A minus vector B, you don't need complicated math at all. You just put their tails together at the same starting point and draw a new connecting line straight from the head of B over to the head of A. That new line, that's your subtracted vector. It's a beautifully simple, elegant trick. So let me ask you, why exactly is velocity considered a vector? Well, think about the displacement of a moving particle. It starts at position r1, and a tiny time interval later, it's at position r2. The change in position is literally just the vector difference between those two distinct points. Because position is a vector, and we are just subtracting two vectors, the resulting rate of change, which is velocity, absolutely must be a vector too.
Part 4. Acceleration on a curve. Okay, so how do we calculate acceleration when a particle is zipping along a complex, curved path? There is a massive trap to avoid here. If we have a velocity vector at time 1, and then further down the curve a velocity at time 2, well, you absolutely cannot subtract them by just connecting their tips while their tails are separated in space. Doing that means absolutely nothing physically. To find the actual, true acceleration, we have to use an elegant geometric solution. We must pick up those two velocity vectors and draw them with their tails starting from the exact same origin point. Now, we can safely draw the connecting line from the head of v1 to the head of v2. That specific line is the true change in velocity, which correctly gives us our acceleration vector. What this all boils down to is that acceleration on a curve actually breaks into two distinct pieces. There's the tangential acceleration, which runs parallel to the path. This simply changes the raw speed of the object, basically like stepping on the gas pedal. Then there's the perpendicular acceleration, acting at exact right angles to the curve. This one doesn't change the speed at all, it only changes the direction, and mathematically it equals the speed squared divided by the radius of the curve. Part 5. The scalar dot product. So out of all this constantly shifting geometry, you might be wondering, is there anything that stays absolutely invariant no matter how we rotate our viewpoint? Actually, yes, there is. Think about the physical squared length of a step in space, calculated as x squared plus y squared plus z squared. That length is completely identical in Joe's system and in Moe's tilted system. This proves an amazing mathematical concept. We can actually extract a purely directionless number, what we call a scalar, straight out of directional vectors. We call this the scalar product, or more commonly, the dot product. It's an operation that takes two directional vectors and brilliantly crushes them down into a single scalar number. Here's how it works. You take the length of vector A, multiply it by the length of vector B, and then multiply all that by the cosine of the angle between them. The resulting number is universally true across every coordinate system. It is completely 100% invariant to rotation. And just to prove I'm not making this up, let's look at how this applies to real, tangible physics. Energy, for example, doesn't have a direction. So kinetic energy is perfectly calculated as 1/2 the mass times the velocity vector dotted with itself. Mechanical work, that's just the force vector dotted with a distance vector. We can even use vectors with a length of exactly 1, called unit vectors, and dot them with other vectors to cleanly slice out specific directional components. It's just a phenomenally powerful system. We've seen today that the mathematical machinery of vectors perfectly captures the symmetry of space. If you move your location or rotate your perspective, the physical laws stay exactly the same, safely encoded in vector algebra. But I want to leave you with a final, slightly provocative thought to chew on. If the physical laws of the universe are perfectly symmetrical across space, are they also perfectly symmetrical across time? Like, does an experiment run today yield the exact same physical laws as an experiment run a billion years ago? Ponder that one for a bit and keep that curiosity alive. Thanks so much for joining me on this explainer, and I'll catch you next time.
Welcome to today's explainer. We're about to go on a really fascinating journey to peel back the very layers of our physical reality. Now, we all toss around the word force every single day, right? But we're going to dig deep into the physics to figure out what actually drives the universe. And honestly, what we're going to find is that the neatly packaged physical laws we all learned in school, well, they often hide a wonderfully messy, complex, and sometimes entirely illusory reality. Let's dive in. So let's start with a really fundamental question. What actually is a force? I mean, it sounds simple enough. We intuitively get the concept of mass, and if we know position and time, we can easily calculate acceleration. But defining force, that is surprisingly tricky. It's actually a deep problem in physics, one that forces us to stop and ask what our mathematical laws actually mean in the real world.
Consider the absolute classic Newtonian definition. Force equals mass times acceleration. F equals ma. It looks perfect, doesn't it? But if we define force strictly as mass times acceleration, we're really just making a circular mathematical argument. We haven't actually learned anything new about nature. Think about it. If we see an object drifting through space, we could just invent a word, let's call it a gorse, and declare that a gorse is causing it to drift. That gives us absolutely zero real information. The true genius of Newton's laws is the idea that force must have its own independent, real-world properties outside of that equation. It has to have a material origin.
To track down those real-world properties, here's our roadmap for this explainer. 1. Beyond F equals ma. 2. The messy reality of friction. 3. The molecular tug-of-war. 4. Fundamental forces in fields. 5. The pseudo-force illusion. And 6. The nuclear force frontier.
Section 1. Beyond F equals ma, the approximation of reality. You see, our perfectly neat physical laws are in fact just approximations of a very dirty, very complex reality. If you insist on a perfectly precise mathematical definition of force, you're never going to get it, because the real world just doesn't operate like an abstract geometry problem. There's a brilliant analogy for this. If you ask a philosopher what an object is, they might just point and say, take this chair, for example. But how certain are you about that chair? Atoms are constantly evaporating off of it. Dirt falls on it, dissolving into the paint. So trying to say exactly which atoms belong to the chair and which belong to the air or the dirt, it's literally impossible. The physical world is a messy mixture. In math, we can perfectly define our axioms. But in physics, we're dealing with reality. Every law we use is a kind of idealization, an approximation of something incredibly complex. Section 2. The messy reality of friction, an empirical illusion. When we look at a familiar, everyday force like friction, or even aerodynamic drag, we immediately see this massive divide between the class ring and reality. The funny thing about friction is that the deeper we study it, and the more accurately we try to measure it, the more complicated and, well, falser the basic equations become. Textbook physics gives us perfectly smooth planes and simple, constant coefficients. But real-world physics? Oh, it involves highly irregular, dirty surfaces. As two bodies slide against each other, microscopic points of contact cling together. Atoms literally snap apart. Vibrations ripple through the material, and heat is generated. It is absolute chaos down on the microscopic level. When we analyze something basic, like a block sliding on a surface, we account for the downward pull, the upward normal force, and the frictional force opposing the motion. In engineering, we use the handy formula F equals mu times N, where mu is the coefficient of friction. But here is the absolutely crucial point. That formula is not a fundamental law of physics. It's just a rough empirical engineering rule. If you take an actual inclined plane and slowly tilt it in a lab, the block won't slide perfectly steadily. It's going to halt, stutter, and accelerate erratically, all because the surface is covered in dirt, oxides, and has varying levels of hardness. In fact, if you try to measure the exact friction of pure copper on pure copper, you run into a totally mind-blowing problem. If you perfectly clean, polish, and vacuum seal 2 pieces of pure copper, getting rid of absolutely all oxides and grease, and then you let them touch, they won't slide. They will literally fuse together, no heat required. Why? Because without impurities separating them, the atoms at the boundary don't know they're supposed to be in separate pieces of metal. They just bond. Section 3. The molecular tug-of-war, the atomic origin. To really grasp what's happening when objects touch, we've got to peel back another layer and zoom way into the atomic level. Everyday friction is ultimately just an illusion caused by vastly complex molecular interactions.
If we track the force between two atoms based on the distance between them, a crazy pattern emerges. At a distance, atoms, even nonpolar ones with completely balanced charges, will slightly attract each other. But if you push them just a bit too close together, that gentle traction suddenly flips into a massive, violent repulsion. That sharp vertical spike in atomic repulsion, that is what is literally keeping you from falling through the floor right now. Now, the really cool part is how this microscopic push and pull creates the rules we experience on a human scale. Think of a standard steel spring. When it's just sitting there, its atoms naturally rest at a distance where those attractive and repulsive forces are perfectly balanced at zero. If you stretch or compress that spring by just a tiny amount, you're only moving the atoms slightly along the very bottom of that force curve, and at such incredibly tiny distances, that curved line mathematically acts basically like a straight line. Because it acts like a straight line, the force you feel becomes directly proportional to how far you pulled it. Macroscopically, we call this Hooke's law. We pat ourselves on the back thinking we found a neat mathematical rule, but really, we are just witnessing a tiny, localized slice of a chaotic atomic tug-of-war.
Section 4. Fundamental Forces and Fields, a New Simplicity.
So we just learned that everyday forces like friction and spring tension get messier the deeper you look. But if we peel back the layers to look at truly fundamental forces like electricity and gravity, something amazing happens. They actually become simpler. To understand these fundamental forces, physicists developed a genuinely brilliant concept, the field. Think about two electrical charges separated by empty space. How on earth do they push or pull on each other with nothing in between? The field concept splits this mystery into two independent parts. First, one object produces a condition in the surrounding space. Second, another object placed in that space responds to that condition. To see this concept in action, imagine an electron beam tube. On one side, a hot filament shoots a stream of electrons straight across. They pass between two metal plates. If we suddenly apply a negative voltage to the lower plate, the beam of light instantly shifts upward. The electrons feel the field condition created by the plate and respond by deflecting away from it. Even more fascinating, if you wiggle a charge to create a field and then suddenly stop, that field keeps propagating outward through space. The field is a very real, tangible phenomenon that literally keeps track of past movements in the universe. Okay, so we've seen how charges respond to stationary fields, but let's ask a wonderfully weird question. What if the observer, the one measuring the force, is the one who is moving or accelerating? This simple question is about to shatter our understanding of reality all over again.
Section 5. The pseudo-force illusion, a trick of perspective.
Whenever an observer is in an accelerating or rotating coordinate system, they experience mysterious pushes and pulls that don't seem to have any physical origin at all. We call these pseudo-forces, and they are entirely a trick of perspective. For instance, picture violently pushing a jar of water forward on a table. As you accelerate it to the right, what happens? The water sloshes backward, standing higher on the rearward side. Now, gravity is pulling the water down, sure, but because the jar is accelerating horizontally, there appears to be a new, mysterious pseudo-force acting horizontally in the opposite direction. The water's surface actually tilts just to balance out both gravity and this phantom push. What's truly fascinating is exactly where this observation leads us. Notice that the pseudo-force acting on the water is exactly proportional to the mass of the water. Well, there's another force we know that is always exactly proportional to mass: gravity. This incredibly deep realization led directly to Einstein's equivalence principle. He figured out that if a person is shut in a box accelerating upward through empty space, they would feel pulled to the floor in a way that is utterly indistinguishable from Earth's gravity. Because of this, Einstein realized that gravity itself might not be a traditional force at all. It might just be an illusion, a pseudo-force caused by the beautifully weird, curved geometry of our spacetime.
Section 6, the nuclear force frontier, the final mystery.
So friction is just molecular noise, and gravity might just be geometry. Now, let's plunge into the final, deepest layer of reality, the nucleus of the atom. This is where all our previous rules just completely fall apart. Look at how incredibly bizarre nuclear forces are. Unlike gravity or electricity, which stretch endlessly across the universe, nuclear forces operate only within an unimaginably tiny range of 10 to the negative 13th centimeters. That's a 0, a decimal point, 12 more zeros, and a 1.
They don't follow Newton's neat inverse square laws. Instead, they die off exponentially the second particles separate. Down here in the quantum realm, the very concept of a mechanical force is basically replaced by quantum mechanical energy interactions. And perhaps the most humbling takeaway of all, the fundamental machinery behind nuclear forces remains entirely unsolved by modern physics.
We've peeled back quite a few layers today, haven't we? We've seen that our trusted mathematical laws are actually just approximations. We saw that friction is a complex atomic illusion. We learned that fields track the history of the universe, and that gravity itself might just be a trick of accelerating geometry. And it leaves us with a truly provocative question to rethink our entire physical reality. If everyday friction is an atomic illusion, and gravity is a geometric pseudo-force, are any of the forces we feel actually real? I really hope this explainer has sparked your curiosity to look at the everyday world just a little bit differently. Keep asking questions and keep peeling back those layers.
Hey everyone, welcome to this explainer. I am absolutely thrilled to get into this material with you today. We're going to be exploring some of the most fundamental, mind-blowing principles in physics, specifically diving straight into Chapter 13 of the legendary Feynman Lectures on Physics. We're setting out on an incredible journey today. We'll start with something incredibly simple, just the one-dimensional motion of a falling block, and we are going to scale that all the way up to the beautiful, mind-bending complexities of the universe, like how the gravitational fields of massive planets actually work. We're going to uncover exactly how energy is conserved, not just when things drop straight down, but when they orbit, when they interact, and when they form giant celestial bodies.
Okay, let's lay out our roadmap. Today we're covering 1. Energy of a falling body, 2. Work done by gravity, 3. Summation of energy, and 4. Fields of large objects.
All right, let's jump right into Section 1, Energy of a falling body. Let's kick things off with our absolute simplest physical setup. Just a classic one-dimensional vertical drop. Imagine just holding an object out and letting it fall straight down. To really lock down what's happening here, we need to establish two fundamental definitions. First, we have kinetic energy, which is simply the energy of motion. If you're a math person, that's 1/2 mass times velocity squared. Second, we have potential energy, which in this simple vertical drop is the energy of position, basically mass times gravity times height. Now, think about what happens when that object drops. As it loses height, its potential energy goes down. But simultaneously, it's speeding up, right? So its kinetic energy goes up. It is a perfect cosmic seesaw. The exact amount of potential energy lost is converted entirely into kinetic energy, keeping the total perfectly, stubbornly constant. Feynman actually calls this a miracle of miracles.
But before we can scale this whole thing up, we need to introduce the concept of work. Now, in physics, work isn't just about exerting effort or breaking a sweat. It's got a very specific mathematical definition. It's the integral of a force along a path, and it's measured in joules. But let's translate that dense math into actual physical meaning. Imagine tallying up every single tiny, microscopic push an object experiences in the exact direction it's moving, all along a specific path. If you're moving exactly in the direction of the force, you're doing work. But here's the crucial part. If you move perfectly perpendicular to that force is doing zero work on you. Keep that little detail in your back pocket, because it's going to be a huge deal in a minute.
So this principle expands beautifully beyond just dropping a block straight down. Think about an object sliding on a curved, frictionless path, like a roller coaster. You might think, well, the changing angles are definitely going to mess up our perfect energy seesaw. But it doesn't. The tangential force, the part of gravity actually pushing the object along the curve, weakens exactly in proportion to the slope of the curve. Because of that perfect mathematical relationship, the rate of change of the kinetic energy is exactly equal and opposite to the rate of change of the potential energy. So whether you drop a ball straight down out a window or let it slide down a twisting, frictionless roller coaster track, that conservation of energy holds beautifully true. Moving right along to Section 2, Work done by gravity. Okay, we're leveling up the complexity now. We are moving from a constant downward force, like gravity in your living room, to a planetary scale. We're talking about the changing, radial pull of the sun or the earth. To explore this, I want to throw a fascinating, almost impossible question your way. Can we build a perpetual motion machine using gravity? Gravity varies, right? It points in different directions depending on where you are in space, and it gets stronger or weaker depending on your distance. So, could we design some perfectly clever, twisting, frictionless track that loops around in space where gravity does more work pulling us in than it takes to pull us back out? Could we come back to the start moving just a little bit faster and go round and round forever? Well, let's break down the answer. Let's model a small mass falling toward a really huge mass. Out here in space, the force of gravity isn't constant anymore. It changes by the inverse square of the distance. But through the magic of calculus, when we integrate that changing force to find the total work done, we actually get a brand new formula for potential energy. As that small mass moves toward the larger one, its kinetic energy increases exactly as this new inverse radius potential energy shifts. The total energy remains completely constant. No free energy yet.
But what about that clever looping track we hypothesized? Imagine moving a small mass around a closed, sort of blocky, jagged track around a massive planet. When we move inward radially, straight toward the planet, gravity does work on us. But consider the segments where we move along a circular arc, perfectly sideways. In those moments, our path is exactly at a right angle to the inward pull of gravity. Remember our definition of work from earlier? Because we're moving perfectly perpendicular to the force, gravity does exactly zero work on those circular arcs. So if you tally up all the radial inward steps where you gain energy and all the radial outward steps where you lose it, they perfectly, mathematically cancel out. The net work for the whole loop is exactly zero.
Now, you might be thinking, hold on, a real orbit doesn't move in a blocky, jagged shape. It moves in a smooth curve, like an ellipse. To see how this holds up on a smooth curve, we can mathematically magnify the path into infinitesimally small, sawtooth jiggles. If we break any smooth curve down to a microscopic scale, the work done going along the slanted, smooth line of the triangle is mathematically identical to the work done going along those jagged, blocky edges. It's the exact same result. So the crucial takeaway here is captured in 3 simple steps. 1, you move radially toward or away from the planet and gravity does work. 2, you move circumferentially, perfectly sideways to gravity, and absolutely zero work is done. 3, when you return to your starting point, I don't care how wild or smooth or convoluted your path through space was, the net work done by gravity is mathematically bound to be zero. Perpetual motion in a gravitational field is simply impossible. A planet returning to the exact same spot in its orbit is always going to have the exact same kinetic energy it had before, period.
All right, section 3, summation of energy.
We are expanding our horizon once again. We've mastered the single falling block, and we've mastered a single planet orbiting the sun. Now we've got to look at the messy, chaotic reality of many, many interacting objects. Think of a massive star cluster or an entire galaxy. When we take all those particles pulling on each other in every possible direction, the mathematics gets intense. You literally have to sum up the energies of every single pair of interacting particles in the system. But when you do all that math, a beautiful simplicity emerges. The total kinetic energy of all the objects plus the mutual potential energy between all the distinct pairs equals a constant. The total energy of this incredibly complex multi-object system remains beautifully constant as long as there's no outside interference. Richard Feynman actually gave us an incredibly helpful mental model to wrap our heads around why this works. Imagine totally empty space. You bring an object number 1 from an infinite distance away. There are no other objects around to pull on it, so it takes exactly zero work. Then you bring in object number 2. Now it's being pulled by object 1, so work is done. Then you bring in object 3. It feels a force from object 1 and from object 2 independently. You just tally up the work done against each force, one by one. By the time you assemble an entire galaxy from scratch, the total work you put in perfectly equals the mutual potential energy of the entire system. It's like a giant puzzle coming together.
Which brings us to our final section, Part 4, Fields of Large Objects.
We're scaling up from discrete individual points of mass to massive continuous expanses of matter. And to kick this off, I want to pose another deeply counterintuitive question. Imagine an infinite flat plane of matter, just a huge, endless sheet of uniform mass stretching in every direction forever. If you are hovering above it, shouldn't its gravitational pull get weaker as you move further away? I mean, think about it. When you launch a rocket away from the Earth, gravity gets weaker by the inverse square of the distance, so it's got to be the same here, right? Well, prepare to have your intuition totally challenged. It turns out our intuition is just dead wrong here. Let's think about hovering just a little bit above this infinite sheet. When you're up close, a lot of the mass right directly under you is pulling you straight down, but mass further out to the sides is pulling you at a really shallow, unfavorable angle, so it doesn't help pull you straight down very much. Now imagine moving twice as far away. Yes, the direct force from any specific patch of mass is absolutely weaker because you're further away. But here's the trick. At this greater height, A much wider cone of mass on the sheet is now situated at a favorable angle to pull you downward. The inverse square drop-off in force is perfectly mathematically canceled out because the amount of mass effectively pulling you increases by the exact same square of the distance.
To put this into perspective, let's contrast these two realities directly. With a point mass, like a standard planet or a star, the force weakens rapidly by the inverse square of the distance. But with an infinite sheet, the gravitational force is a complete constant. It is totally independent of distance. Whether you are 1 single meter above the sheet or 1 million miles above the sheet, it exerts the exact same gravitational pull on you. No difference whatsoever.
And that brings us to what is basically the climax of this entire explainer. What happens when we take a giant sheet of mass and wrap it into a hollow sphere? Think about a thin spherical shell of mass. The mathematics behind this produces what is, without a doubt, the absolute miracle of classical mechanics. Let's break down this spherical shell miracle, because it's wild. First, if you're floating anywhere outside this hollow shell, the gravitational pull you feel is exactly the same as if every single ounce of the shell's mass were magically crushed into a single tiny point at the exact dead center. That's literally why we can calculate the orbit of the moon just by measuring from the center of the Earth. But the second fact is even more mind-blowing. If you were to somehow climb inside this hollow shell, the gravitational pull from all the walls around you perfectly cancels out. It doesn't matter if you're hovering right near the edge or floating perfectly in the middle, the potential energy is constant everywhere inside, which means there is zero net force. You would float completely weightlessly inside, feeling absolutely no gravitational pull whatsoever.
This explainer has taken us from the simple drop of a falling block all the way to the majestic mathematics of celestial spheres. We've seen how energy behaves in simple, straight lines, along twisting, frictionless curves, through the deep void of space, and even inside impossible infinite structures. So I want to leave you with this final provocative thought. We know that mathematically, a solid planet is just an infinite series of these hollow spherical shells nested inside one another, basically like a giant cosmic onion. Given the absolute miracle we just learned about what happens inside a hollow shell, what does that mean for the gravitational force experienced by an object sitting at the exact dead core of the Earth? I'll let your mind spin on that one. Thank you so much for joining me today, and keep exploring.
Picture this, you're trying to hold a really, really heavy box. Let's say it's 100 pounds, perfectly still, right in front of you. Within minutes, you're sweating, your arms are shaking, and you are just completely exhausted. But here is a massive, almost frustrating paradox. According to the strict equations of physics, as long as that box isn't moving, you are doing absolutely zero physical work. None. 0 joules. So if physics says you aren't doing any work, why on earth is your body reacting like you just sprinted up 5 flights of stairs? Well, welcome to this explainer, where we're going to unravel this paradox and completely transform how you view energy, effort, and the invisible forces that shape our universe.
Now, to actually solve this, we've got to take a quick detour into biology, because the physiological feeling of effort is totally different from true physical work. See, human arms are made of what's called striated muscle. When you're holding that heavy box, your muscle fibers don't just lock rigidly into place. Instead, your nervous system is firing off these massive volleys of impulses. Individual muscle fibers are doing these rapid, tiny twitches and then relaxing. You're trembling because those volleys are irregular, and honestly, they're incredibly energy draining. But contrast that with a clam. A clam uses smooth muscle to keep its shell snapped shut. It can just lock that muscle into a set position for hours against a huge pulling force, and it does it completely effortlessly. It's literally using 0 energy. Just like a wooden table holding up a heavy weight, no physical work is actually being done once it's locked in place.
So welcome to our explainer on Chapter 14 of the Feynman Lectures on Physics, focusing on work and potential energy. Today, we're going to take some incredibly dense foundational mathematical formulas and translate them into highly intuitive physical realities. We'll leave our biological quirks behind and explore what physical work actually means, how the universe stores its energy, and why, at the deepest levels of reality, no energy is ever truly lost.
Here is our roadmap for today. First, what is physical work? Second, paths and conservative forces. Third, calculating potential energy. Fourth, where does energy go? And finally, moving from forces to fields.
All right, Section 1. What is physical work?
Let's leave that sweaty box behind for a second and look at the formal definition. In physics, work isn't about the effort you feel, it's entirely about movement. Specifically, it's force multiplied by distance. But there's a huge catch here. Imagine a block sliding down a frictionless curved track. There are multiple forces at play. Gravity is pulling straight down, and the track is pushing up against the block, which we call the force of constraint. But here is the secret to physical work. Only the component of force in the exact direction of displacement actually counts. Because the constraint force of the track pushes precisely perpendicularly at a right angle to where the block is moving, it does absolutely zero work. None. So, when we're calculating the change in the block's kinetic energy, we can completely ignore the track's push and just focus on the work done by gravity.
Moving on to Section 2, Paths and Conservative Forces.
This strict definition of work builds into one of the most beautiful, maybe even kind of crazy concepts in physics: conservative forces. This is basically the idea of forces where the journey completely ceases to matter. By definition, a conservative force is one where the total work done in moving an object between 2 points is entirely independent of the path taken. Think about that for a second. Whether you take a straight line, a jagged zigzag, or some massive looping detour, the energy math works out to be exactly the same. Gravity is the absolute perfect example of this predictable, path-independent behavior. Imagine pushing an object through a conservative force field from point 1 over to point 2. You could run the numbers, integrating the force times the distance along a nice, smooth, direct route. Let's call it curve A. Or you could take this totally chaotic, looping curve B. The wild thing is, if you do the math, you yield the exact same number of joules of work either way. The actual journey is completely irrelevant. Literally only the start and end points matter. Next up, Section 3, Calculating Potential Energy. Because the path doesn't matter for these special conservative forces, we get to establish this built-up, position-based value called potential energy. It's essentially energy that's stored purely by virtue of where an object happens to be located. And we can calculate this stored energy across all sorts of different scenarios. For uniform gravity, like dropping an apple from a tree, the potential energy is simply mass times gravity times height. If you're compressing a linear spring, the stored energy is half the spring constant times the distance squared. And out in the cosmos, between distant planetary point masses, it's negative big G times the two masses divided by the distance between them. That last formula is actually the exact math that tells us why a rocket needs exactly twice as much energy to permanently escape the Earth as it does to just orbit it. Pretty amazing, right?
Now, let's zoom way in, down to the microscopic scale. If you map out the potential energy between two oxygen atoms, it reveals this absolutely fascinating curve. When they're far apart, they attract each other, pulling closer and sliding right down this potential energy slope. But if they get too close, they intensely repel, shooting back up the left side of the curve. Ultimately, they find a stable equilibrium right at the very bottom of the dip, which is labeled D here. That lowest point is where they just settle down into a cold oxygen molecule. It requires absolutely no force to stay there, kind of like a marble just resting peacefully at the bottom of a bowl. And as we venture beyond classical mechanics and get into quantum mechanics, something wild happens. The very concept of a force starts to get really clunky. Actually, it literally dissolves. When modern scientists study nuclear matter or complex molecules, they almost never draw little arrows representing forces anymore. Instead, potential energy becomes the primary, universal language of atoms. Energy is quite literally the ultimate currency of the universe. Which brings us to Section 4, where does energy go? So this raises a massive question. If we slide a block across a rough table, friction eventually slows it down until it stops entirely. The kinetic energy seems to just vanish, right? Does friction somehow break the rules of conservative forces and steal our energy away? No way. The crucial takeaway here is that this is entirely an illusion of loss. Friction absolutely doesn't destroy energy, it just hides it. When that block slides and eventually stops, its macro-level motion is just transforming into invisible, chaotic kinetic energy at the atomic level. The atoms inside the block and the table are just jiggling faster and faster. We obviously can't see this microscopic jiggling with our eyes, but we can feel it. We experience it as heat. The energy isn't gone, it's just put on a microscopic disguise.
Finally, Section 5, From Forces to Fields. Okay, time for our final conceptual leap. We're going to completely change our perspective from individual objects physically pushing each other to a continuous grid of potential energy that fills all of space. Instead of trying to track a million complex 3D force arrows, mathematicians use this brilliant trick. Step 1. They map out a simple scalar field, which is really just a single number representing the potential energy at every point in space. Step 2. They take what's called a partial derivative, which basically examines exactly how steep the energy slope is in the x, y, and z directions. Step 3.
They invert the sign. And just like that, from a super simple map of energy, you can extract the exact complex 3D force vector pushing an object at any given coordinate. It's an incredibly powerful mathematical tool known as the gradient.
Let's look at a fascinating real-world example of this mathematical trick in action: the gravitational potential created by a hollow spherical shell of matter. Outside the shell, the potential energy curves downwards, pulling objects toward it just like a normal planet would. But look really closely at the inside of the shell, from 0 to radius a. The line is perfectly flat. The potential energy is completely constant. And because force is just the slope of the potential energy, a flat slope means zero force. If you were floating around inside this hollow shell, you would experience absolutely no gravitational pull in any direction whatsoever.
And the best part? These exact same rules apply flawlessly to electricity. In a capacitor, which is just two parallel metal plates, there is a constant electric field between them. If you take a tiny electrical charge and push it against that field from plate 2 over to plate 1, you are doing work. You are actively building up potential energy. In the world of electricity, the difference in that potential energy between the two plates is simply what we call voltage. It's the exact same physics, just a different flavor. All of this builds to one of the most profound realizations in modern physics, which was perfectly captured by Richard Feynman. He stated, "The total energy of the world, kinetic plus potential, is a constant when we look closely enough." When we strip away our crude macro-level view of the world, we find that at the fundamental atomic level, non-conservative forces completely cease to exist. Every single interaction is perfectly conservative. Every single drop of energy is meticulously accounted for in the grand ledger of the universe.
So I'm going to leave you with this final thought. Look around the room you are sitting in right now. Everything might appear perfectly still, right? But if every fundamental interaction perfectly conserves energy and absolutely nothing is ever truly lost, what invisible, microscopic motions, what hidden jiggling of atoms transferring heat and light and potential are silently happening all around you, right at this very second, just to balance the cosmic ledger? Thanks for joining me on this explainer. Keep wondering, keep looking closer, and I'll see you next time.
Welcome to This Explainer. Today we're diving deep into Chapter I-15 of the source material to decode the actual physical meaning behind Einstein's special theory of relativity. We're not just going to stare at equations here, we're talking about the tangible, mind-bending ways that space, time, and mass literally warp to keep the universe functioning. So let's get right into it.
Okay, here's our roadmap for the journey. We'll start off with the principle of relativity, check out the Michelson-Morley mystery, explore the illusion of time, look into shrinking space and fractured simultaneity, and finally, wrap up with the equivalence of mass energy.
All right, part 1, the principle of relativity. So, let's set the stage with the baseline rules of the universe. You know, the ones everyone agreed on for over 200 years. Because to understand exactly where physics broke down, we first need to get how it was supposed to work. Picture two entirely different setups. On one hand, we've got Joe. Joe is just standing completely still on the ground. On the other hand, there's Mo, and Mo is moving uniformly forward in this smoothly flying spaceship. In physics terms, these are two completely separate coordinate systems. One is stationary, and one is cruising at a constant speed.
Now, the really fascinating thing here is that mechanical laws, they behave exactly the same for both of them. You actually can't feel your own uniform motion. Think about it. If Mo plays a game of pool in his smoothly gliding spaceship, those balls bounce exactly like they would if you were just hanging out back on Earth. If he doesn't have a window to look out of, there is literally no physical experiment he can do to prove he's moving. And that right there is the classic principle of relativity. Everything works perfectly, well, until we bring light into the equation.
Which brings us to part 2, the Michelson-Morley mystery.
So back in the 19th century, scientists noticed a huge problem. Light just didn't seem to play by Newton's rules. If you shoot a beam of light from a speeding car, classical physics tells us the speed of the light and the speed of the car should simply add up. I mean, it makes logical sense, right? Plus, physicists figured, hey, just like sound needs air to travel through, light waves must need some physical medium to ripple through. They called this invisible cosmic ocean the ether. So naturally, they set out to measure the Earth's absolute speed moving through this hypothetical ether by checking for variations in the speed of light.
To catch this ether wind, scientists built this brilliant apparatus in 1887. It's the famous Michelson-Morley experiment,
and it basically pitted two beams of light against each other in a literal drag race. They used a light source, a partially silver glass plate, to split the beam, and two mirrors set at exactly equal distances.
Now here's the physical logic behind the whole setup. Because the Earth is hurtling through space, we're talking orbiting the Sun at a whopping 18 miles per second, the apparatus itself is moving incredibly fast. Therefore, a beam of light traveling parallel to that motion should experience a sort of drag, right? It should take a different amount of time to return than a beam traveling perpendicular to the motion. Basically, the Earth's movement through the ether was supposed to throw those two light beams completely out of phase.
But guess what? The result was a complete null. Both beams arrived at the exact same time. It was honestly as if nature was engaged in this active conspiracy to hide the Earth's absolute velocity. This experiment proved that the speed of light is always exactly the same, no matter how fast your source is moving. Light just travels at roughly 186,000 miles per second, period. And that meant something was deeply, profoundly wrong with the foundational equations of physics.
All right, part 3, the illusion of time. So to fix this impossible glitch in the universe, scientists realized they had to rethink something fundamental, the rigid ticking of a second itself. Because if the speed of light absolutely refuses to change, well, something else has to give. Imagine a clock that ticks every time a pulse of light bounces straight up and down between two mirrors. For Mo, who is traveling inside the moving ship, that light just moves in a simple, straight vertical line. But for Joe, watching from the outside as the ship flies past, that light beam is physically dragged forward. To his stationary eyes, the light is forced to trace a much longer, diagonal zigzag path.
But remember our rule. Light absolutely refuses to change its speed. So if the light has a further distance to travel along that diagonal path, but it's moving at the exact same constant speed, there is literally only one mathematical solution. Time itself must slow down on the moving ship. And this isn't just a mechanical trick of the clock. To the outside observer, Mo's heartbeat, his aging, even the literal time it takes him to light a cigar, it's all happening in slow motion just to keep the universe's math balanced.
And we know for a fact this isn't just theory, thanks to muons. These are cosmic particles created about 10 kilometers up in our atmosphere, and they naturally die in exactly 2.2 microseconds. At their normal speed, they should decay long before they ever hit the ground. Yet, they survive long enough to reach the Earth's surface, purely because their extreme speed slows their internal clocks. Because they are traveling so close to the speed of light, their time slows down relative to us, which allows them to clear that immense distance. It's almost like real-life time travel.
Moving on to part 4, shrinking space and fractured simultaneity.
Okay, so time slowing down? That's really only half the equation. To explain why those Michelson-Morley light beams arrived simultaneously, a physicist named Lorentz proved that the longitudinal arm of the apparatus actually, physically, shrank as it moved. We call this the Lorentz contraction. If a meter stick flies past you at a ridiculously high speed, it is literally shorter than a meter to your eyes. And let me be clear, this isn't an optical illusion. Space itself tangibly compresses in the direction of travel to ensure the speed of light remains perfectly constant.
So because time slows down and space shrinks, our whole concept of things happening at the same time completely shatters. Let's say Mo flashes a light in the exact middle of his ship. It hits the front and back clocks simultaneously for him. But for Joe outside, the moving ship's back wall is rushing forward to meet the light, while the front wall is running away from it. So two perfectly synchronized events for Mo are completely out of sync for Joe. The word simultaneous is no longer a universal truth. It depends entirely on how fast you are moving.
And finally, part 5, the equivalence of mass-energy. This brings us to what I like to call the ultimate trade-off in the universe. Isaac Newton believed that a constant force could accelerate an object forever, but Einstein proved that the speed of light is an absolute cosmic speed limit. Nothing can break it. So, if you keep pushing an object that's nearing light speed, where does all that newly added kinetic energy go if it can't make the object go any faster? Well, it converts directly into mass. The faster you go, the heavier you physically become.
We actually see the physical reality of this in particle accelerators today. Take the synchrotron at Caltech, for example. Electrons are pushed so incredibly close to the speed of light there that their mass violently balloons. They become 2,000 times heavier. They are literally packing the mass of a proton. If we didn't carefully account for this extreme weight gain using Einstein's math, the magnetic fields just wouldn't be strong enough to steer them, and the machines would fail entirely.
Einstein took this idea to its absolute monumental conclusion. If adding motion energy to an object makes it physically heavier, then an object's resting mass itself must just be a highly concentrated form of dormant energy. Mass and energy, they aren't different entities at all. They are literally just two forms of the exact same thing. The total energy content of matter equals its mass multiplied by the speed of light squared. E equals mc squared. The terrifying scale of that math became a very physical reality with the atomic bomb, because the speed of light squared is such an unfathomably huge number, multiplying it by even a tiny bit of mass yields an almost incomprehensible amount of energy. The devastating, city-leveling explosive power of a 20-kiloton bomb comes from the total annihilation and conversion of just 1 single gram of matter. Let that sink in. After the explosion, the remaining material is exactly 1 gram lighter.
So, here's a thought to leave you with. If time, space, and mass are just fluid illusions shaped entirely by your speed, what does that mean for your reality right now? Thank you for joining us for this explainer. We hope this journey leaves you deeply questioning the very fabric of the room you're sitting in right now. What you perceive as solid, constant, and predictably ticking away is actually entirely fluid. Keep questioning, keep learning, and we'll catch you next time.
All right, welcome to the Explainer. Today, we're taking a completely mind-bending journey through one of the most fascinating, reality-altering topics in all of physics, relativistic energy and momentum. We're going to unlock Richard Feynman's brilliant, purely mechanical proof of relativity, drawing straight from Chapter 16 of his legendary lectures.
Okay, let's dive into this. Here's our roadmap. We'll start off with philosophy versus reality, move on to the famous twin paradox, discuss the speed limit of space, explore mass and velocity, and finally prove that energy actually has mass.
All right, part 1, philosophy versus physical reality. So relativity is incredibly famous, right? But it's also deeply misunderstood, especially by what Feynman hilariously calls cocktail party philosophers. Henri Poincaré actually hit the nail on the head with this quote. He said, according to the principle of relativity, the laws of physical phenomena must be the same for a fixed observer as for an observer who has a uniform motion of translation. The absolutely crucial point here is that relativity isn't just some vague, wishy-washy idea that everything is subjective. No, it is a strict, precise principle. It means the fundamental laws of physics stay mathematically identical whether you're standing perfectly still or moving smoothly in a straight line.
Now, this really highlights the divide between armchair philosophy and actual hard physics. There's this myth floating around that because we can't feel our movement, absolute velocity is totally meaningless. But physics relies on experimental facts. Now, it's absolutely true that we can't detect uniform, straight-line motion without looking out a window. But we can, for sure, detect rotation or acceleration. Think about it. If the room you're sitting in right now suddenly started spinning, you'd literally be thrown against the wall. We know the Earth rotates because of physical experiments, like the Foucault pendulum. Physics cares about what we can actually measure.
Moving right along to Section 2, Time and the Twin Paradox.
Because we experimentally cannot detect uniform motion, that inability completely warps our experience of time. Let's set up a classic thought experiment. Imagine we have Peter, who stays perfectly stationary down on Earth, and his twin brother, Paul, who blasts off in a spaceship at a ridiculously high speed. Because Paul is moving so incredibly fast relative to Peter, Peter observes something completely bizarre. From his vantage point on Earth, all of Paul's clocks seem to run slower. His heartbeat, his thoughts, his aging, the whole shebang just slows down.
But wait a second. If motion is truly relative, couldn't Paul just sit in his ship and claim that he's the one standing still, while Peter and the entire Earth are the ones hurling away? And if that's the case, shouldn't Paul see Peter aging slower? So, when Paul turns the ship around and they finally reunite, who is actually older?
Well, the answer is Paul is younger. Actually, scratch that idea of it being a symmetrical illusion. The paradox gets broken by absolute physical acceleration. For Paul to come back and compare ages, he had to physically turn his spaceship around. He felt those rockets fire, he felt the G-force push him against the seat. Peter felt absolutely nothing back on Earth. The one who experiences the absolute acceleration is the one who ages less. And hey, this isn't just a fun theory. In labs, we've accelerated these tiny particles called muons in magnetic circles and demonstrably proven that they live significantly longer than stationary ones. It is a hard, measured fact of our universe.
Okay, Section 3, the speed limit of space. Now, you might be wondering, if time itself stretches and bends depending on your speed, what happens to the way we calculate speed itself?
Well, it bends too. In everyday math, if you're on a train going 50 miles an hour and you throw a baseball forward at 50 miles an hour, that ball is going 100 miles an hour relative to the ground. Simple, right? But relativity totally breaks everyday math. If you're in a spaceship going half the speed of light and you fire a rocket forward at half the speed of light, that rocket does not reach the full speed of light. Because time and distance are actively warping, half plus half doesn't equal 1. Mathematically, it equals exactly 4/5. Nothing can break that ultimate speed limit. No exceptions.
And what we're looking at here really brilliantly illustrates why this happens mechanically. Imagine a light clock that bounces a photon up and down, right next to a physical particle clock doing the exact same thing. Because this whole setup is moving sideways to the right, from the perspective of someone standing outside watching, that light ray has to travel on a longer diagonal path. But since the speed of light is a strict constant, traveling that longer diagonal path simply takes more time. And since the physical ticks of the particle clock have to match the light clock, the particle's upward vertical speed must physically slow down from that outside perspective. Moving sideways literally limits how fast you can move up and down.
Which brings us to Section 4, the mass-velocity connection. Okay, we are now completely ready for the absolute core visual proof of this explainer. We're going to show mechanically, step by step, exactly why mass itself has to increase as an object speeds up. Let's start with this perfectly symmetric setup. We've got an elastic collision between two identical objects. Let's just call them two protons. They're flying toward each other at the exact same speed in opposite directions. Because their speeds and masses are totally identical, the total momentum here is exactly 0. They hit and they bounce off at the exact same speeds. Notice how all the arrows are the exact same length. It's a perfectly balanced, beautiful little collision. But to really wrap our heads around relativity, we've got to shift our perspective. This right here is the real trick of Feynman's deduction. Step 1, we just established our balanced zero-momentum collision. Now, step 2, we are going to look at this exact same crash, but imagine we're watching it while driving by in a car. Specifically, a car moving horizontally at the exact same horizontal speed as one of those particles. Now, what's really interesting here is how the collision changes from our moving car's point of view. Look at particle number 1 down at the bottom. Because our car is matching its horizontal speed perfectly, to us, particle 1 doesn't look like it's moving sideways at all. It just looks like it's shooting straight up, bouncing, and coming straight back down. Meanwhile, particle 2 is flying by at a terrifyingly fast horizontal speed on a super steep angle. So here is the absolutely crucial takeaway. We know from the fundamental laws of physics that vertical momentum absolutely has to be conserved. It has to balance out. But remember what we just learned with that moving clock? When things move horizontally at high speeds, their vertical velocity appears to slow down. Particle 2 is moving much faster horizontally than particle 1, which means its upward vertical velocity is technically slower than particle 1's. Now, momentum is just mass multiplied by velocity, right? If particle 2's vertical velocity is lower, but the vertical momentum still perfectly balances out against particle 1, there is literally only one possible mathematical reality. The mass of the faster-moving particle must be greater. The only way for momentum to balance across different viewpoints is if mass itself physically increases with velocity. And that brings us to our grand finale. Section 5, Energy has mass. That last point was a massive breakthrough. Let's take this brand new rule that a moving object literally gets heavier and apply it to a totally different kind of crash, an inelastic collision. We have two identical objects, each with a resting mass we'll call m0. They're speeding towards each other, carrying a ton of kinetic energy. They collide right in the center and violently stick together, forming a brand new, completely stationary blob of matter, which we'll call Big M. So, what is the mass of M? Normally, you'd probably assume the mass is just the two rest masses added together, right? 2 plus 2 is 4. But in reality, the mass of this new object, M, is actually greater than the rest masses of the two original objects combined. How is that possible? Well, because those objects were moving rapidly before the crash. They had increased mass due to their high velocity. When they slammed together and stopped, that extra mass didn't just vanish into thin air. The pure kinetic energy of their motion was trapped inside that new composite object and literally converted into actual, physical, measurable mass. This proves that energy itself has inertia. Energy is mass.
So let's take this whole concept and see how it logically builds into literally the most famous equation in history, E equals mc squared. Feynman's purely mechanical deductions lead us directly right here. We don't even need to separate rest energy, kinetic energy, or potential energy anymore. They're all just different flavors of mass. If you heat up a gas, you're adding energy, so it physically gets heavier. If you forcefully smash particles together, the resulting object is heavier. And the reverse is true too. If you split a heavy atom like uranium into smaller pieces, the lost mass is violently converted back into energy, which is the exact real-world principle behind atomic fission. It's just an incredible total paradigm shift in how we view reality. So as we wrap up, I want to leave you with this provocative thought to chew on. If all energy is simply mass, and mass is just tightly packed energy, how much hidden explosive energy do you think is locked away inside the perfectly still everyday objects sitting right in front of you on your desk? It's a universe-altering perspective, all deduced from the simple logic of things crashing into each other. Thank you so much for joining me on this explainer, and keep questioning the physical world around you.
Welcome to This Explainer. Today, we're taking on something absolutely mind-bending. We're going to translate Volume 1, Chapter 17 of the legendary Feynman lectures on physics into a purely visual geometry. If you've ever felt like relativity is just this massive jumble of confusing equations, well, you're definitely in the right place. We're going to look at this geometrically. We'll treat space and time not as totally separate ideas, but as a single, mappable reality. It's a real game changer. Okay, let's just quickly breeze through our roadmap for today. First, we're mixing space and time. Second, mapping space-time geometry. Third, the universal space-time interval. Fourth, past, present, and future. And finally, the power of four vectors. Let's get right to it.
Section 1. Mixing space and time. A shift in perspective.
To really wrap our heads around relativity, we literally have to throw out our everyday intuitive ideas about how we measure reality. So I want to pose a question to you right off the bat. How does reality change when we just change our perspective? Think about looking at an everyday object. Your brain automatically processes what you're seeing, right? But the actual measurements of what you see depend entirely on where you're standing. Richard Feynman gives us this absolutely brilliant analogy for this. When you look at an object, you'd say it has a certain width and depth. But if you just take a few steps to the side and look at it from a totally different angle, well, what was once depth kind of becomes width, and vice versa. They get all mixed up. Width and depth aren't fundamental built-in properties of the object itself. They just depend on your viewing angle. And the craziest part, the exact same thing happens with space and time. Just as walking around an object mixes up its width and depth, moving at really high speeds mixes up space and time. The only reason we don't feel this intuitively every day is just because, we aren't casually walking around at the speed of light. So to talk about this bizarre new reality, we kind of need some new vocabulary. We have to picture a world where space and time are perfectly mixed into a single geometrical entity, space-time. A specific point in this space-time, meaning an exact physical position at an exact moment in time, is what we call an event. And a physical object, it isn't just a 3D dot. It takes up space, sure, but it also lasts for a certain amount of time. It forms a continuous line, or what Feynman playfully calls a blob, that extends through this massive four-dimensional world.
Section 2. Mapping space-time geometry. Drawing the blob.
Let's actually see what it looks like to draw these blobs on a map. This perfectly illustrates movement in 4 dimensions. The horizontal axis is space, and the vertical axis is time. Now, check out line A. That right there is a particle completely at rest. But notice, even though it isn't moving in space, it is still hurtling forward, parallel to the time axis. It's always moving through time. Line B is a particle moving at a constant speed, sort of drifting outward. Line C shows a particle slowing down. You can see its path curving. And line D, that fixed, perfectly straight slope, that is the ultimate speed limit of the universe, the path of a beam of light. Now, this brilliantly illustrates what happens when things suddenly change. Like, say, a particle disintegrating into 2 brand new particles, which is that forked line you see right there. You might naturally think that to view this from the perspective of a moving spaceship, you just tilt the space and time axes like a standard, everyday geometry problem, which is what you see crossed out at the bottom. But actually, scratch that. Ordinary Euclidean geometry completely fails us here, because space and time mix differently. They literally use different mathematical signs. The whole geometry of space-time forces us to totally rethink how we draw moving axes in the first place.
Section 3. The universal space-time interval. The rule of C.
So, if regular geometry doesn't quite work, how on earth do we measure distance? Well, to make the math of space-time elegant, we have to measure space and time in the exact same units. We can literally measure time in meters. Seriously,
A meter of time is simply the time it takes for a beam of light to travel exactly 1 meter. And to put that into perspective, that is exactly 3.3 billionths of a second. By setting the speed of light, or c, to equal exactly 1, space and time are finally put on an equal footing.
So the absolutely crucial point here is how we calculate distance in this new world. In our normal 3D space, you'd find the distance squared by adding up the squares of the x, y, and z coordinates. Simple enough. But in space-time, the universal property that everyone agrees on, no matter how ridiculously fast they're moving, is called the space-time interval. Here, you take the time squared, and you actually subtract the spatial dimension squared. Because of those minus signs, this interval can be 0 or even negative. There's literally no way that happens in regular geometry. It's an entirely new system that gives actual physical meaning to the absolute limits of our universe.
Section 4. Past, Present, and Future. The light cone. Now, this whole negative and zero interval business isn't just some mathematical trick. It dictates the actual physical reality of the universe. It completely redefines our concepts of past, present, and future. This hourglass shape right here is called a light cone. Those diagonal lines represent the exact path of light starting from a zero interval. What this diagram does is literally separate the entire universe around a single event, let's call it point O, right at the center, into completely distinct regions, all based on that ultimate speed limit of light. So space-time gets split into 3 specific zones of causality. Region 2, down at the bottom, is the effective past. Everything down there could have traveled slower than light to reach point O right exactly now, meaning it can actually affect us. Region 3, up top, is the effective future. That means we could shoot a bullet or send a laser signal from point O and actually influence those future events. But Region 1, the areas on the sides, those are called space-like intervals. Since absolutely nothing can travel faster than light, we can't affect Region 1 right now, and it definitely can't affect us. It is fundamentally, physically disconnected from our present moment. Feynman beautifully summarizes the sheer reality of this disconnection. When we look up at the star Alpha Centauri, we're seeing it exactly as it was 4 years ago. Wondering what it's doing right now is entirely an illusion. Because light takes 4 years to reach us across that massive gap, Alpha Centauri's now is completely stuck in that unobservable Region 1. A universal right now across the whole universe? It just doesn't exist in physics? No way.
Section 5. The power of 4 vectors, unifying the physics.
Okay, so we've mapped space and time, but what about all the physical stuff inside it? Well, just like time and space transform together, so do momentum and energy. Notice how the momentum of a moving particle is represented here as a tangent arrow right along its path. The spatial directions of the arrow represent the particle's physical momentum, but look at the vertical time component of that exact same arrow. That actually represents the particle's energy. It's wild. This whole concept is called a 4-vector. To preserve the fundamental laws of physics across every moving coordinate system in the universe, basically, to make sure the conservation of momentum actually holds true everywhere, we absolutely must include a time component. Energy physically acts as the time component for a particle's 3D spatial momentum. You simply cannot have momentum without energy, just as you can't have space without time. They are forever intrinsically bound together. And with that, we've basically mapped out a complete mathematical unification of the universe. Hermann Minkowski, the brilliant mathematician who actually laid the geometric groundwork for relativity, delivered this poetic conclusion perfectly. He said that through 4 vectors and the spacetime interval, space and time as independent concepts simply vanish. Only a kind of union between them remains.
So I'm going to leave you with this incredibly provocative challenge directed from Feynman himself. We know for sure that we can't observe the now of Alpha Centauri because it lies out there in the disconnected space-like interval. But what if we could? Would any paradox be produced if it suddenly became possible to know things that are in those space-like intervals? Think about the totally mind-bending consequences of knowing the unobservable present and how the speed of light is literally the only thing keeping cause and effect perfectly in order. Keep exploring, keep questioning, and thank you so much for joining me on this explainer.
All right, let's jump right into this explainer. Today, we're cracking open Richard Feynman's legendary lectures, specifically chapter I-18 on two-dimensional rotation. It's a bit mind-bending sometimes, but we're going to decode the mechanics behind everything from a swirling galaxy down to the water flowing out of your tap. When the physical world gets messy, it honestly gets incredibly interesting. So we're going to master the fundamental rules of this whirling world by really understanding the physical meaning behind the math. To do that, we're just going to follow a clear 5-part path, starting off with the center of mass, moving into the kinematics of rotation, understanding torque, exploring angular momentum, and wrapping up with conservation and inertia. Let's do it.
Part 1, the center of mass. Basically, the absolute simplest aspect of motion. Picture this. You grab some weird, clunky object. Let's say it's just a bunch of wooden blocks, spokes, and strings all glued together, and you just chuck it into the air. As it flies, it's jiggling, it's wobbling, twisting every which way. But we know from basic physics that a simple particle always follows a perfect, smooth parabola when you throw it. So if this weird, blocky thing isn't a simple particle, what exactly is tracing that perfect parabola? I mean, it's not the corner of a block, it's not the tip of a spoke, yet something inside that wobbling mess is on a totally predictable path.
And that's something. That's the center of mass. It's essentially an artificially invented mathematical point right somewhere in the middle of the object. If you throw the object, this imaginary point moves in a flawless parabola. If the object is just floating out in deep space with no forces acting on it at all, it might be twisting and jiggling like crazy. But its center of mass, it stays completely still or just coasts at a constant velocity. Finding this point is a massive relief, honestly. It means we can entirely ignore the object's straight-line, linear movement and focus 100% of our attention on the internal journey, the turning.
Okay, part 2, kinematics of rotation, learning the actual language of turning.
Feynman does something absolutely brilliant here. We don't need to invent totally new physics from scratch. We literally just map the exact same concepts we already know from one-dimensional linear movement right onto two-dimensional rotation. So instead of linear distance, we look at the angle, how far the body has spun around. Instead of velocity being how far it moves in a second, we get angular velocity, how much that angle changes in a second. And acceleration, that just becomes angular acceleration. It's a perfect one-to-one translation.
Now, to see how linear and rotational movement actually connect, think about an object turning from an origin point. If you have a single particle inside that object, sitting some radius away from the center, and the whole object turns by a tiny angle, that particle gets carried along for the ride. Because of how we define angles and radians, the actual physical distance that particle moved through space is exactly its radius multiplied by that change in angle. By translating that geometry into a physical formula, we get something beautifully simple. If you divide that distance by the time it took, you find that the magnitude of the particle's velocity is simply its angular velocity multiplied by its radius. It makes total intuitive sense, right? The further out from the center axis you are, the faster you literally have to physically travel just to keep up with the turning of the whole object.
All right, moving on to part 3, understanding torque, the twisting force.
To keep our perfect linear analogy going, we need a rotational equivalent for force. In a straight line, work equals force times distance. But for rotation, we define a brand new tool called torque to be our twisting force. So our new rule is that work equals torque multiplied by the angle the object turns through.
Now, imagine applying a force to a point on a spinning object. If you push at a weird angle, you can always break that push into 2 parts, one pointing straight out away from the center axis and one pointing tangentially along the edge. Here's the kicker. If you push straight toward or directly away from the axis, you get absolutely zero twist. It doesn't help it spin at all. It is strictly the tangential component of your push that actually creates the torque. So the crucial takeaway here is that torque is the magnitude of the force multiplied by something called the lever arm. The lever arm is just the perpendicular distance from the axis of rotation to the line of your force. And you know what? This simple mathematical reality explains exactly why a longer crowbar gives you so much more twisting power. You're increasing the lever arm, which dramatically cranks up the torque, even if your muscles are pushing with the exact same amount of physical force. Which brings us to part 4, angular momentum, the momentum of a spin. Let's zoom in on a single particle zooming through space. Maybe it's a whole planet orbiting the sun, or literally just a speck of dust. It's moving along some curve. What is its rotational momentum? Its angular momentum, relative to a center point. Well, just like torque relies on the lever arm of the force, angular momentum relies entirely on the momentum lever arm. You just take the regular, straight-line momentum of the particle, and you multiply it by the perpendicular distance from the center axis to the line of that momentum. Feynman beautifully isolates this core truth with a simple rule. He says what counts for angular momentum is not how fast it is going away from the origin, but how much it is going around the origin. Just like we saw with torque, any motion pointing dead straight out from the center contributes absolutely nothing to the spin. The twisting effect only cares about the motion traveling in a circle around your axis. And this leads to a pretty stunning realization about Kepler's famous law of planetary motion. You know, the one that says planets sweep out equal areas in equal times? Why does that happen? Well, because the force of gravity from the sun pulls straight in. It's completely radial. There is zero tangential force, meaning exactly zero torque is being applied to the planet about the sun's axis. And because there's no torque, the planet's angular momentum stays perfectly constant. The math of that constant angular momentum translates directly to the planet sweeping out the exact same area of space in equal amounts of time, no matter where it is in its weird elliptical orbit.
Finally, Part 5, Conservation and Inertia. Let's look at collections of particles.
Think about all the millions of atoms inside a rigid body, just pushing and pulling on each other constantly. It sounds mathematically impossible to track, right? But Newton's law of action and reaction actually saves us here. Every internal push has an equal opposite push exactly along the same line. And because they're on the same line, their lever arms are perfectly identical. That means all those internal torques completely cancel each other out, pair by pair, straight to zero. This is a massively powerful theorem. The total angular momentum of an object changes only if an outside, external torque is applied. We can study the overall motion without getting bogged down in the internal atomic machinery. But here is where rotational mechanics gets truly wild compared to straight-line linear mechanics. In a straight line, your inertia, meaning your resistance to being moved, is just your mass, and your mass never changes. But in rotation, your inertia is called the moment of inertia. And while your overall mass is a fixed number, your inertia for turning changes drastically depending on how far away your mass is from the axis of rotation. Imagine a spinning rod with two sliding weights on it. If you slide those weights close to the center axis, the rod spins up pretty easily. But if you take those exact same weights and slide them all the way out to the very ends of the rod, it dramatically slows down the acceleration. The system hasn't gained a single ounce of mass, but it has gained way more resistance against turning, simply because the mass is farther away from the center. And this brings us to the ultimate payoff. Since angular momentum has to be conserved when there's no outside torque, your moment of inertia multiplied by your angular velocity has to stay constant. This equation is the exact physical meaning behind the famous ice skater effect. When a spinning ice skater pulls their arms in, they aren't losing mass, but they are intentionally dropping their moment of inertia. Because that inertia goes down, their spin velocity absolutely must skyrocket to balance the equation and conserve the total angular momentum. Which leaves us with something truly profound to think about. Whether you're tossing a wobbly block of wood, watching an ice skater pull off a dizzying spin, or looking through a telescope at a massive galaxy collapsing inward and whirling faster and faster, it is all the exact same math. It's the same physics. These deeply intuitive rules of two-dimensional rotation we explored today seamlessly scale up to shape the entire universe. It's really just force, lever arms, and momentum working together in a beautiful, endless dance. Thanks for joining me on this explainer. Keep your eyes open and keep noticing the physics of the whirling world around you.
Welcome to The Explainer. Today, we're unpacking something that is just fundamentally mind-bending: three-dimensional rotation. We're going to lean heavily on the incredible framework Richard Feynman laid out, specifically in Chapter 20 of his famous lectures, to really completely demystify the so-called magic of spinning objects. We're getting right down to their actual physical meaning.
Here's our game plan. We'll start with the gyroscope mystery, get into the math of 3D twists, break down the anatomy of precession, explore something called the nutation wobble, and wrap it all up with the rotation of solid bodies.
All right, Section 1, the gyroscope mystery.
Let's kick things off with a question that completely defies our everyday intuition. Seriously, why doesn't a spinning top just fall over? I mean, when you let go of a gyroscope, gravity and common sense tell us it should flop straight to the floor instantly, but it doesn't. Instead, it seemingly floats and precesses sideways. To figure out why, we need to talk about angular momentum.
Picture this. You're sitting on a perfectly frictionless swivel chair holding a rapidly spinning wheel with its axle totally horizontal. Since it's horizontal, there is absolutely zero angular momentum in the vertical direction. But watch what happens if you tilt that wheel straight up. Boom! Suddenly, the wheel has vertical angular momentum.
Because the total vertical momentum of the entire system has to stay at zero, nature instantly compensates. You and the chair are forced to spin in the exact opposite direction to balance the whole thing out. It's a perfect illustration of conservation in action.
Moving right along to Section 2, the math of 3D twists. To really decode this magic trick, two-dimensional math just isn't going to cut it anymore. We have to introduce a new tool called the cross product. Unlike ordinary math, the cross product of two vectors gives you a brand new vector that is perfectly perpendicular to both of the original ones. Honestly, it's kind of a miracle of good luck that 3D space lets us represent a complex twist on a plane as a single clean line pointing at a right angle to it. It behaves exactly like a right-hand screw. You turn the screw, and the direction it advances is your new vector.
But we have to make a really crucial distinction here between our vectors. We have what physicists call honest polar vectors. Think of things like force or velocity, which describe a true, straight-line physical direction. On the flip side, things like torque and angular momentum are pseudovectors or axial vectors. They're basically artificial mathematical constructs that rely entirely on our right-hand rule convention just to neatly capture these rotational twists.
Okay, Section 3, Anatomy of Precession. Let's take those math tools and apply them to the actual physical forces inside the wheel. Notice how when you apply a horizontal force to tilt the axle, our cross-product math dictates that it creates a vertical torque. And this vertical torque means the angular momentum vector changes direction, but importantly, not magnitude. The wheel doesn't speed up or slow down. Instead, that vertical twist forces the wheel to sweep sideways. That right there is precession. But mathematically proving it and physically feeling it are two different things.
So let's look directly inside the wheel, because this is where the physical reality really clicks. As the wheel spins and precesses sideways at the exact same time, the individual particles inside aren't moving in simple flat circles anymore. The particles that cross the precession axis are forced to travel in curved paths, and to force a particle along a curved path requires lateral force. So as you push on the axle, that force is communicated through the spokes right to the rim, pushing particles on one side and pulling them on the opposite side. We can easily generalize this to our rapidly spinning top. Gravity acts on the top center of mass, basically trying to yank it straight down. But because the tip is anchored to the floor, that downward pull acts as a horizontal torque. Following our cross-product rules, that torque ends up pointing sideways at a perfect right angle to gravity, which sends the top into that really familiar circular cone-like sweep.
The absolute most crucial takeaway here is that none of this is magic. It's an incredibly precise balancing act. That sideways precession is simply the macroscopic, visible result of lateral forces pushing and pulling on millions of individual particles inside the solid structure, ultimately keeping the net force perfectly balanced at zero.
Which brings us to Section 4, the nutation wobble.
But hold on. If gravity is actively pulling down on the top, why doesn't it just drop downwards a little bit before those sideways forces actually take over? Well, keep Feynman's brilliant grounding words in mind here. A gyroscope is a wonderful thing, but it is not a miracle. Because we are about to reveal the hidden truth. The gyroscope actually does fall.
Yeah, you heard me right. When you first let go of a spinning gyroscope, it instantly starts to drop straight down under gravity. But as it falls, it begins to turn. It actually overshoots its steady sideways velocity, rises back up a bit, and traces this tiny looping cycloidal path. Imagine a pebble stuck in the tread of a rolling tire. It's exactly like that. This tiny, incredibly rapid wobble is called nutation, and it happens so fast your naked eye usually can't even register it.
Let's step through that rapid sequence real quick. The gyroscope drops, that fall creates the turning motion. It loops back up, and finally friction damps the wobble down into a smooth, steady sweep. But check out step 4. It settles slightly lower than where it initially started. By yielding just that tiny bit to gravity, the gyroscope generates the exact amount of vertical angular momentum it needs to fuel its steady sideways precession forever. It literally has to dip in order to sweep.
And finally, Section 5, Rotation of Solid Bodies.
Let's zoom way out and see how this logic applies to literally every rigid body out there. If you mount a wheel lopsidedly on an axle, it's going to shake violently when you spin it. That's because its angular velocity and angular momentum vectors point in entirely different directions. The bearings have to constantly apply torque just to keep the whole thing from flying apart. But contrast that with a totally irregular shape, like, say, a lumpy potato. Surprisingly, even a potato has 3 perfect, mutually perpendicular axes built into it, called principal axes. So to sum it all up, angular momentum isn't always perfectly parallel to angular velocity. When they don't align, you get violent shaking and wobble.
But if you can find a solid body's principal axes, those perfect, inherent lines of symmetry, and spin it exactly along one of them, well, the vectors align perfectly. The wobble completely disappears, leaving you with clean, mathematically beautiful, and rock-stable rotation.
Wrapping up the explainer today, we've seen that by breaking down the vector math, really looking at the internal forces on individual particles, and discovering that hidden drop of the notation wobble, we've completely demystified the so-called magic of the spinning top. There are no miracles here. It's just spectacular physics working exactly as it should.
I'm going to leave you with one final thought to ponder. Now that you know the secret of the cross product and you understand these principal axes, how do these invisible right-angle forces dictate the motion of practically everything around us? I mean, from the spinning toys on a playground, to the stabilizing wheels keeping satellites alive in deep space, all the way up to the slow, steady wobble of the Earth itself. It's all the same physics. Thanks for joining me on this explainer, and remember to keep looking for the physics hidden in plain sight.
Welcome to today's explainer. We're about to go on an absolutely incredible intellectual journey. We're going to trace a path that starts with something we all do, counting on our fingers, and ends up unlocking the actual geometric shape of the physical universe. It's an amazing puzzle of abstraction, so let's see if we can follow the breadcrumbs together.
Okay, let's dive right into our map for today's explainer. We'll trace the rules of mathematics, use abstraction to break those rules, compute the irrational, witness the final invention, and ultimately see how algebra meets physical geometry.
Section 1. The Rules of Mathematics. Setting the board. Let's start right in the middle of mathematical history.
So, our starting pieces on this board are the integers, the basic counting numbers. Now, we're assuming we already know how to count, right? We're completely skipping the deep philosophy of what a number actually is, and we're just going to use these as our foundational building blocks.
From just simple counting, we can derive a sequence of direct operations. First, if we count units successively, we define addition. Second, if we start with nothing and add a number to itself successively, well, we define multiplication. And third, if we start with 1 and multiply successively, we define raising a number to a power. Notice how beautifully each operation just naturally builds directly upon the previous one.
Now, what's really interesting about this slide is the pattern it reveals. For every direct action we invent, we naturally seek a way to undo it backward. Addition gives us subtraction. Multiplication brings us division. And taking a power, well, that branches into two inverse operations, roots and logarithms. And let me tell you, it's these undo buttons that are about to drastically stretch our entire mathematical universe.
Moving on to Section 2, Abstraction and Generalization, Breaking the Rules.
All right, I want you to consider this puzzle. What is 3 minus 5? According to our own definition of subtraction, we need a number that when added to 5 gives us 3. But if our universe only contains positive counting numbers, we've hit a massive wall. We are completely stuck.
So, to bypass this wall, we rely on a truly great plan, abstraction and generalization. We invent negative numbers. We simply stretch our number line backward below 0. But here is the absolute genius part of it all. We demand that these brand new, totally abstract numbers obey the exact same algebraic rules as our regular integers. And miraculously, it actually works.
But enjoy that victory while it lasts, because we immediately hit another wall. What is 3 divided by 5? Once again, using only the integers we have, this is an impossible division. There is no whole number in existence that can solve this.
The solution? We expand the board yet again. We invent rational numbers, literally just ratios, or fractions, and we lean on that same grand strategy. We just assume these new fractions follow our original algebraic rules of addition and multiplication. And sure enough, everything hums along beautifully. The grand plan works perfectly.
Which brings us to Section 3, Computing the Irrational, the Logarithm Journey. Now, imagine throwing this historic problem at the ancient Greeks. What is the square root of 2? They were completely stumped by this. Why? Because absolutely no fraction on Earth, no neat ratio of whole numbers, can form a square whose area is exactly 2. It's a non-repeating decimal that just goes on forever. To move forward, we are forced to invent irrational numbers.
And actually computing these irrational numbers was a massive headache. Back in the 17th century, a mathematician named Mr. Briggs sat down and calculated successive square roots of 10 entirely by hand. Just think about the tediousness of that.
He took a square root, then the square root of that result, effectively dividing the power by 2 each time, all the way down to the 1 over 1024 power. And through this, he noticed that as the power gets infinitesimally small, the results start approaching a very specific relationship.
So the crucial point is this specific constant that emerges out of the bottom of his calculation, 2.3025. It's this incredibly awkward multiplier that just haunts base 10 logarithmic calculations. But mathematicians realize something brilliant. If we simply change our starting base from 10 to a different specific number, we can force that messy multiplier to become exactly 1. That magical base is the number e. By shifting to the natural base e, our calculus and physics equations suddenly simplify beautifully.
All right, on to section 4, the final invention, the last wall. We're building up to something big here.
We've invented negatives, we've got fractions, and we've conquered irrationals. But now, what is the square root of -1? Really think about this for a second. If you square a positive number, you get a positive. If you square a negative number, you also get a positive. So squaring no rational or irrational number we've ever discovered can possibly equal -1. It's completely impossible under our current rules.
To solve this, we are forced to invent one last concept, the imaginary number I, which is defined entirely by the property that its square is -1. Combine that with real numbers, and this gives us complex numbers. And this right here is the most fantastic miracle in mathematics. With complex numbers, we ensure that we never ever have to invent a new type of number again to solve algebraic equations. Every single equation can now be solved. We've officially hit the ceiling. It is the final invention.
And that leads us to section 5, algebra meets physical geometry, visualizing the impossible. As you'll see on this slide, if we take our base and raise it to an imaginary power, tracking the real and imaginary parts as x and y values, something truly incredible happens. As the power increases, the values don't just shoot off into infinity. They oscillate. They swing down, past 0, go negative, and return. They repeat. By purely tracking an imaginary exponent mathematically, we generate the exact same sine and cosine waves that dictate the physical swinging of a pendulum or the alternating current running through your wall.
And this brilliantly illustrates the final unification. We can plot any complex number on a plane. The horizontal axis is our real number, and the vertical is our imaginary number. But geometrically, this point isn't just a simple x and y coordinate. It's a radial distance, r, and an angle of rotation, theta. Our purely abstract algebra is literally mapping out physical rotations in space.
This entire breathtaking journey gives us Euler's joule. E to the power of I times theta equals cosine theta plus I times sine theta. It is widely considered the most remarkable formula in mathematics. I mean, we started with this simple idea of counting on our fingers, and just by strictly following logical rules of abstraction, we unlock the geometric, oscillating patterns of the physical universe. It leaves us with a deeply provocative thought. Is mathematics just a handy tool we invented? Or is it the fundamental language the universe was written in, long before we got here? I'll let you ponder that. Thanks for joining me on this explainer.
All right, let's just dive right into this. Today, we're walking through a truly fascinating explainer on how a single, specific mathematical concept acts as kind of a master key, one that unlocks the physical realities of basically the entire universe. We are going to be exploring Chapter 23 of the legendary Feynman Lectures on Physics, which is entirely dedicated to the profound and, honestly, mind-bending topic of resonance. So, we're starting with a bit of a mystery today. I mean, think about it. What could an exploding volcano possibly have in common with the electrical circuits in your computer or a gamma ray shooting out of an atom? It sounds like the setup to a really nerdy science joke, right? But the answer actually lies in a single, incredibly elegant phenomenon that governs almost everything that vibrates, swings, or oscillates in our reality. So here's our roadmap for cracking this code today. First, we'll look at the magic of complex numbers. Second, the damped forced oscillator. Third, electrical resonance equivalency. Fourth, resonance in everyday nature. And finally, we'll wrap up with quantum and subatomic resonance. Okay, let's get into it. Section 1. The magic of complex numbers. To really analyze physical phenomena that oscillate, physicists pull off this brilliant little trick. Basically, we represent oscillatory forces as the real parts of complex functions. This lets us bypass all the messy sines and cosines. Imagine a force pushing a pendulum back and forth.
If you use traditional trigonometry, tracking that motion through calculus becomes this absolute nightmare of endless massive equations. Instead, physicists kind of pretend the force has an imaginary part and use exponential functions. I know, it sounds totally absurd to use imaginary numbers for real-world physics, but it is an incredible shortcut.
And this visually captures exactly what we're talking about. We can plot these complex numbers on a plane, with a real axis and an imaginary axis. Thanks to the magic of Euler's formula, instead of tracking a rigid x and y coordinate, you get a radius r and a phase angle theta. This perfectly, seamlessly models something that is spinning or oscillating continuously over time.
But here is the crucial payoff. When we use these complex exponentials, differentiating an equation just means multiplying it by I omega. That's it. It turns tangled, headache-inducing calculus into basic stackable block algebra. Dr. Feynman actually points out that this mathematical sleight of hand is almost as big of a breakthrough as the invention of logarithms. You can literally look at a complex differential equation and solve it by sight, just by dropping down a multiplier.
Moving right along. Section 2, the damped forced oscillator.
Now, applying that math gives us the ultimate fingerprint of resonance. Check out that massive spike in amplitude on the left. As the frequency of your pushing approaches the natural swinging frequency of the system, which we label omega 0, the energy just shoots way, way up. Now look over at the right. At that exact same peak moment, the phase shifts drastically. That means the system goes from actively resisting your pushes to perfectly syncing up with them. It's a total game changer.
The width of that peak you just saw, that is entirely determined by friction, which is represented by the Greek letter gamma. If friction is very small, the response shoots straight upward near the natural frequency, creating this razor-sharp, highly tuned peak. Think about a playground swing. If it had absolutely zero friction, mathematically that peak would go to infinity. Like one good push would eventually send a kid into orbit. But you know, in the real world, drag dictates exactly how wide or sharp that resonant spike actually becomes.
Let's switch gears a bit. Section 3, Electrical Resonance Equivalency.
So just as a physical mass oscillates on a spring, electrical charge oscillates back and forth through a circuit. Notice the basic elements isolated on the left there. We've got capacitors, resistors, and inductors. When you wire them together in a loop, like the setup on the right, and drive it with an alternating voltage, the electricity literally sloshes back and forth. It behaves exactly, and I mean exactly, like our physical pendulum.
This mapping is mind-blowing. It acts as a universal translator, proving this profound truth. The exact same mechanical math perfectly maps onto electrical circuits. The physical mass is exactly the electrical inductance. The friction is electrical resistance, and the stiffness of the spring is the exact inverse of capacitance. What this means is, if you understand how a rusty swing set works, you inherently understand the math inside a multi-million-dollar computer motherboard.
As Feynman so brilliantly highlights, nature speaks one mathematical language. The equations governing that swinging pendulum are literally identical to the ones tuning your car radio. Electrical engineers use what they call complex impedance to design circuits, but if you strip away the jargon, underneath, it is fundamentally the exact same algebraic trick we just learned from moving physical objects.
So where else do we see this? Section 4, Resonance in Everyday Nature.
Let's look at a massive planetary scale. The Earth's entire atmosphere acts as a giant oscillator driven by the Moon's gravity, and it produces this exact same resonance curve. The Moon pulls the atmosphere into a tide, and the whole sky essentially slushes back and forth. We actually managed to measure the natural frequency of this giant atmospheric oscillator when the Krakatoa volcano exploded in 1883. It was an explosion so ridiculously powerful it rang the Earth's atmosphere like a giant bell, with a period of about 10.5 hours. And guess what? That perfectly matched the mathematical resonance models.
Now, let's zoom all the way into the microscopic scale. We find the exact same curve inside a tiny grain of salt. A salt crystal is basically just a lattice of positive and negative charges. By firing an infrared electric field at it, we push those charges back and forth. Right at the resonant frequency, the crystal absorbs the most energy. Notice that deep, unmistakable dip in the transmission curve right at 60 microns? That is the exact, undeniable fingerprint of resonance.
All right, let's go even deeper. Section 5, Quantum and Subatomic Resonance.
When we bombard lithium atoms with protons, that resonance fingerprint appears yet again. But this time it's mapped on an energy scale instead of frequency. Why? Because in the weird world of quantum mechanics, energy and frequency are fundamentally the exact same thing, linked directly by Planck's constant.
When those incoming protons hit the precise energy level required to trigger a nuclear reaction, the yield of gamma rays spikes into that classic razor-sharp resonant peak.
10 billion. Let that number sink in for a second. In the Mass-Bauer effect, we find a nuclear energy level with a staggering quality factor, or Q factor, of 10 billion. To put that in perspective, the Q factor is just a measure of how narrow and sharp the resonance peak is and how long the ringing lasts. A basic mechanical swing might have a Q of 5. A really well-made tuning fork, maybe a Q of 1,000. This nuclear resonance is so unfathomably sharp that its Q factor is 10 billion. If it were a physical pendulum, you'd push it once, and it would keep swinging for thousands of years.
This incredibly delicate measurement represented the sharpest resonance of any oscillator ever recorded, a discovery totally worthy of the Nobel Prize it won. Because the peak is so infinitesimally narrow, the researchers couldn't just tune a dial to find it. They had to physically move the radioactive source at a snail's pace, literally just a few centimeters a second, using the tiny Doppler effect of that physical motion to slide the frequency right into that impossibly sharp resonant dip. Absolutely brilliant.
Finally, we actually use this universal curve to discover entirely new states of matter. Physicists identify strange subatomic particles, like the K- meson, simply by finding this resonant bump in their collision data. When they crash particles together at near light speed, a sharp resonance indicates a very specific, volatile energy state. In the quantum world, that mathematical bump in the data is the literal, fleeting existence of an entirely distinct particle.
So, as we wrap up this explainer, I really want you to consider what other invisible, universal connections are secretly vibrating right in front of us. From a kid on a playground swing, to tuning a radio, to the very fabric of subatomic matter, it's all connected by this brilliant mathematical master key. The universe truly speaks one language. I hope this sparked your curiosity today, and I highly encourage you to keep observing those hidden patterns all around you.
Hey everyone, and welcome to this explainer. You know, usually in physics, we spend a ton of time studying driven systems, like a pendulum being actively pushed back and forth. But what happens the exact millisecond you literally cut the power source? I mean, the energy doesn't just vanish, right? It enters this fascinating, entirely inevitable process of winding down. So today, we're diving right into Chapter 24 of Feynman's lectures to explore transients. We're going to uncover the hidden mathematical and physical reality of a damped harmonic oscillator when it's left entirely to its own devices. Okay, so here is our roadmap for today's explainer. First up, energy and the Q factor. Second, math meets physical reality. And third, visualizing electrical transients. Let's just jump right in.
All right, part 1, energy and the Q factor. So, to really ground this, let's go back to that initial super relatable question. What actually happens to a pendulum when you just stop pushing it? When that external driving force is totally removed, all that stored energy doesn't just poof out of existence. The kinetic energy of its motion and the potential energy of gravity are still actively trading places back and forth. But with every single swing, air resistance and internal friction act as a damping force. The energy losses that used to be compensated for by your active pushing are now eating directly into the system's stored reserves. And this winding down phase, that is our inciting incident. And hey, that brings us to a formal definition. In physics, a transient is a solution of the differential equation when there is no force present, but the system isn't simply at rest either. To put that in everyday terms, a transient is basically a system left entirely to its own devices, just bleeding out its stored energy. It's this temporary state, a bridge between being actively driven and finally coming to a complete dead stop. Now, you've probably noticed that some systems wind down almost immediately, right? While others seem to keep going and going for ages. How do we actually measure that difference? Well, enter the Q factor. The Q factor isn't just some dry math formula. It's a direct measure of pure physical efficiency. Mathematically, it's defined as the ratio of the total energy stored in the oscillation compared to the amount of work lost per radian of the cycle. Basically, a high Q factor means the system is a fantastic hoarder of energy. If a system has a Q factor of, let's say, 1,000, it means it only loses a tiny fraction of its energy per swing. It will ring like a perfectly struck bell for a really, really long time after that initial strike. Moving on to Section 2. Math meets physical reality. Richard Feynman walks us through this with his characteristic elegance, and he actually treats it almost like a story. To solve the equation of this dying wave, physicists use a clever little 3-step trick. Step 1. They guess a complex exponential solution. Why? Because as Feynman notes, an exponential is the absolute easiest thing to differentiate in calculus. And let's face it, physicists love a good shortcut. Step 2. By plugging this guess in, the math spits out 2 different roots, or 2 possible answers. And then step 3, to make this usable in the real world, we have to combine our answer with its complex conjugate.
But wait, why do we even need that third step? I absolutely love this insight from Feynman. He points out, the equation does not know that we are arbitrarily going to take the real part. The physical world has a real solution. Think about that. The math is just happily chugging along in the complex plane, dealing with imaginary numbers. It doesn't automatically know that a real physical pendulum can't swing in an imaginary direction. So we have to deliberately build a real-world wave by blending the complex mathematical answer with its mirror image, its complex conjugate. By adding them together, the imaginary parts cancel out perfectly. And boom, we're left with a solid, real physical wave.
And this perfectly illustrates the exact results of all that math. The solid wavy line represents the actual physical position of our system over time, like the real-world swinging of our pendulum. But notice the dashed lines kind of forming a boundary on the top and bottom? That is the mathematical envelope. It's the exponential decay curve we just derived, and it perfectly tracks the physical decay of the wave. The total energy shrinks smoothly, while the physical object bounces back and forth inside that shrinking boundary until it just stops.
All right, on to our final section, visualizing electrical transients. To really visualize this practically, we get to use one of the most powerful translation techniques in all of physics. It turns out a mechanical system and an electrical circuit follow the exact same mathematical rules, literally the same. The physical mass of an object maps perfectly onto electrical inductance. The physical friction, the air resistance acting as a damping force on our swing, maps directly to electrical resistance. And the physical stiffness of a spring, that becomes the capacitance of our circuit. To the differential equations, a bouncing weight on a spring and a surging electrical circuit are totally identical. Which means we can actually build this. We have a simple electrical circuit designed to perfectly mimic a mechanical transient. By suddenly closing the switch, we inject voltage right into the inductors and capacitors. It's the exact electrical equivalent of pulling a weight on a spring down and letting it snap back. The energy just starts sloshing back and forth. And because it's electrical, we don't have to just guess what it looks like. We can actually hook it up to an oscilloscope and watch the mathematical transient wave drawn on the screen in real time. So let's see this theory in practice through some actual oscilloscope traces. In the first example, we have what's called an underdamped system, a high Q factor with very, very low electrical resistance. The wave just bounces back and forth freely, slowly decaying. But in the second example, as we turn a dial to increase the electrical resistance in the circuit, notice how much faster the wave dies out. The increased friction forces a much steeper decay envelope, basically bleeding the system's energy out rapidly. So here's the crucial point. What happens if we keep pushing it? What if we crank the resistance up to an absolute extreme? In the first highly resistant setup, the friction is so intense you only get one struggling gasp of an oscillation before it completely dies. And in the final setup, that is exactly what happens when resistance crosses a critical threshold into what we call an overdamped state. The math actually shifts. The part of the equation that causes the oscillation gets totally overpowered by the damping, and the imaginary numbers vanish entirely. You are left with pure, smooth, exponential decay and zero oscillation. It's literally the equivalent of trying to swing a pendulum while entirely submerged in thick honey. It doesn't swing back and forth, it just slowly oozes to the center and stops. And that, really, brings us to our profound takeaway for this explainer. The physical world always finds a way to present a real solution, perfectly bridging the gap between abstract, scribbled equations and the hard reality we can actually measure. Whether it's the mechanical slowing of an underdamped harmonic oscillator or the electrical decay of an engineered circuit, the universe operates on these beautifully consistent mathematical rules. So the next time you notice a sound fading away or a vibration coming to a gentle halt, I hope you can visualize the invisible math pulling it gracefully to rest. Thank you so much for joining me on this explainer. What hidden mathematical patterns will you notice in the world around you today? Keep wondering and definitely keep exploring. All right, let's dive right into this explainer. Today, we're exploring the absolutely fascinating world of geometrical optics. And specifically, we're diving deep into the true physical meaning of light as laid out in Chapter 27 of the legendary Feynman Lectures on Physics. We're going to unpack the invisible mechanics, the sheer real-world physics behind the lenses that power everything from your everyday glasses to your smartphone camera to cutting-edge microscopes. And, this isn't just about memorizing some dry equations. It's about really understanding exactly how we manipulate the journey of light.
But before we even touch the math, we really got to ask ourselves two fundamental questions. First, how do we actually wrangle and manipulate light to reveal things we can't see with the naked eye? And, perhaps a bit more surprisingly, do the absolute laws of physics even allow for a flawless, perfect lens to exist? As we'll see, the answer to that second question fundamentally limits everything we do in optics.
Here is our roadmap for today. We'll start with the geometry of light, move on to focusing with spherical surfaces, see how to build a thin lens, scale up to magnification and compound lenses, and finally we'll hit the ultimate limits. Okay, let's jump into section 1, the geometry of light. It all begins with the single most fundamental constraint in optics, which is grounded in the principle of least time. Think of light traveling to a focus point like a race. The straight path, right down the middle, is the shortest and fastest route. But any light taking a diagonal path from the outer edges, that route is physically longer. Through some basic geometry, we know that extra distance is roughly the height squared divided by twice the base distance. Now, why does this matter? Well, it's absolutely crucial, because if we want a crisp, sharp image, the light taking that outer, longer route and the light taking the direct, shorter route must arrive at the exact same time. So, how do we level the playing field? We can't speed up the outer rays, right? That's physically impossible. Instead, we have to deliberately slow down the center rays. We do this by putting a sort of speed bump in the way, passing a light through a medium like glass. The factor by which this material slows down the speed of light is called its index of refraction, or n. For example, if n is 1.5, light travels 1.5 times slower in that glass than it does in an empty vacuum. This is, hands down, our primary tool for manipulating light. Moving right along to section 2, focusing with spherical surfaces. The trick now is figuring out exactly how to shape that glass to create the perfect time delay across the entire surface. If we shape a single curved surface separating air and glass just right, we create a real image. That means every ray from a starting point is bent to perfectly converge at a new point deep inside the glass. But what happens if the object is just too close to the surface? The rays get bent, sure, but they still diverge. They're essentially pushed beyond parallel. But here's the cool part. If you trace those diverging rays backward, they appear to originate from a completely phantom point behind the glass. We call this an apparent, or virtual image. It's essentially a localized, physics-approved optical illusion. And you've actually experienced this virtual image effect yourself. If you've ever stood at the edge of a swimming pool and looked straight down, the bottom looks significantly shallower than it really is. The flat surface of the water is literally bending the light rays as they exit into the air, tricking your brain into thinking they originate from a higher point. Thanks to water's specific index of refraction, the pool appears to be exactly 3/4 of its actual depth. Crazy, right? Now, keeping track of all these bouncing, bending light rays can get messy real fast. So to keep from losing their minds, physicists use a clever little cheat code, a simple sign convention. Basically, object distances to the left are positive and image distances to the right are positive. It's just a standardized, foolproof way to ensure our equations work out perfectly every single time, whether we're dealing with real images, virtual illusions, or mirrors. Which brings us perfectly to section 3, creating the thin lens. Now that we've got a handle on a single surface, let's step it up to the actual lenses we use every day. A standard thin lens is really just a 2-for-1 deal. It's the exact same math of a single curved surface, just applied twice in a row. You take the light hitting the first surface, figure out where it hypothetically wants to focus, and then you use that point as the starting source for the second surface. You're literally just chasing the light through the glass. And this is the physical reality of the thin lens, because the light rays hitting the outer edge have to travel a physically longer path through the air. The rays going straight through the middle need to be held back. That precise thickness, that extra chunk of glass right in the center, acts as a highly tuned time delay mechanism. It ensures the straight path and the diagonal path take the exact same amount of time to reach the focal point. That right there, that is the true magic of a lens. Let's zoom out a bit for section 4, magnification and compound lenses. Because, as we know, lenses don't just focus tiny dots of light, they recreate whole, magnified pictures of our world. So how do we figure out exactly how big an image will be?
Well, by tracking just two specific VIP rays, often called paraxial rays, we can map it out instantly. The first ray goes in parallel to our axis and comes out cutting right through the focal point. The second ray does the exact opposite. It goes through the focus first and comes out parallel. The exact spot where those two rays cross gives us the precise height and placement of our magnified image. It's a beautifully elegant geometric trick.
But what if you have a massive telescope or a compound microscope with 10 different lenses stacked together? You'd think the math would spiral out of control, right? Incredibly, it doesn't. Any complex sequence of lenses can be mathematically simplified down into just two principal planes. As long as you measure your focal lengths from these two imaginary planes, that entire bulky optical system acts mathematically just like one single thin lens. It's an absolute lifesaver for optical engineers. And that brings us to our final stop, Section 5, the ultimate limits. Because as beautiful as all the geometry we've discussed is, geometrical optics is at the end of the day just an approximation, and it has some very strict physical boundaries. Remember when we talked about the perfect shape for a lens? Ideally, it's a complicated fourth-degree curve, but those are incredibly hard and expensive to manufacture, so we compromise. We use easy-to-make spheres instead. But that compromise costs us. It creates spherical aberration, a literal smearing of the image because the outer rays miss the true focus point. Throw in chromatic aberration, where different colors of light travel at slightly different speeds in the glass and focus at completely different spots, plus off-axis smearing, and you start to see exactly why professional camera lenses need so many different pieces of glass just to correct for these real-world errors. But let's pretend for a second you're a genius designer. You perfectly correct all those aberrations. Flawless glass. You are still going to crash headfirst into an absolute, insurmountable wall called resolving power. If you're looking at a microscopic bacterium with two tiny spots on it, at a certain point, no matter how much you crank up the magnification, those two dots will just blur into one. Geometrical optics assumes light rays are perfectly straight little lines, but the reality is, they aren't. And this is where Chapter 27 drops a profound realization on us, straight from Richard Feynman himself. Light is an oscillating wave. Once the time difference between the rays traveling through your perfectly crafted lens is smaller than the actual wave oscillation, the period of the light itself, geometrical optics completely breaks down. There is physically no use improving the lens any further because the fundamental wave nature of light takes over, hopelessly smearing the points together. Which leaves us with a truly mind-bending question. If the absolute finest glass lenses in the world can only take us as far as the physical wavelength of visible light allows, what completely different physics and what completely new types of machines are we going to have to invent to see beyond that limit, deep into the atomic world? It's a provocative thought, and it marks the true hard boundary of geometrical optics. Thanks so much for joining me on this explainer today. I hope it helped illuminate the physics of light for you.
Welcome to the Explainer. Today, we are tackling one of the absolute most profound syntheses in human history. We're going to be looking at Chapter 28 of the Feynman Lectures on Physics, all about demystifying electromagnetic radiation. We're embarking on this really fascinating, high-energy journey into the physical reality of how light and radio waves actually work. It's an incredible story, really, about how the entire universe is seamlessly knit together by fields and forces.
So, here's our roadmap for today. 1. Knitting the universe together. 2. The law of radiation. 3. The dipole radiator. 4. Interference and vectors. And 5. The unsolved mystery.
All right, let's jump right into Section 1, knitting the universe together. I want you to consider this for a second. How is it that electric surgings in a galaxy, say 5 billion light years away, literally some of the farthest objects we've ever detected, how can they still have enough influence to physically move the electrons right here in our eyes? Or, drive the currents in the giant dish of a radio telescope? It's a profound, almost philosophical mystery of interconnectivity.
To wrap our heads around this, we really need to look back at the grand 19th century synthesis. At the time, we already knew that gravitational forces drop off as the inverse square of distance, and the exact same is true for static electrical fields. They also drop off as the inverse square. Now, because of this, their influence fades super rapidly over vast distances. But then James Clerk Maxwell comes along. He noticed this inconsistency when he was trying to unify the laws of electricity and magnetism, and to fix it, he added this brilliant mathematical term. It's a radiation term, but instead of the inverse square, it drops off much more slowly, as the first power of distance. And that first power term? It's the magic key. It's literally the missing link that allows signals to travel across the vastness of the universe.
Which brings us to Section 2, the law of radiation.
Now take a look at this massive, kind of terrifying formula, equation 28.3. This is the complete electric field equation, and it's got three main parts. First, you have the delayed Coulomb field. Second is a rate of change correction. But here's the thing. Both of these rely on the inverse square of distance, meaning they just fade out way too fast. So if we're studying light and radio waves over long distances, we can actually strip those first two terms away entirely. All the radiant effects we actually care about come strictly from that third term, the retarded acceleration of the charge, which varies inversely as the first power of distance.
So, boiling it all down, the crucial point is that we only need to care about this single, magically simple equation right here, equation 28.5. It tells us that radiation depends purely on the acceleration of the charge projected onto what we call the plane of sight. Basically, if you imagine looking at a moving charge from a distance, it's just the side-to-side acceleration that you can actually see from your perspective that matters.
But, there's a catch. We have to talk about retarded time. Because light has a universal speed limit, we never actually see where a charge is right now. The delay time is just the distance, r, divided by the speed of light, c. Richard Feynman had this brilliant metaphor for it. He said, observing a moving charge is like looking at a painter who is painting a delayed scene. A real painter paints what he sees now, sure, but in physics, everything we react to is the charge's past acceleration. We are literally looking back in time.
Moving right along to Section 3, the dipole radiator. Let's see how this actually works.
Okay, let's dive into this physical setup. What we've got here is a high-frequency signal generator, and it's connected to two pieces of wire, labeled A and B. The generator creates a potential difference that pulls electrons out of one wire and aggressively pumps them into the other, over and over, rapidly reversing. This forces a massive number of charges to accelerate up and down together. Because the wire is short compared to the distance light travels in a single oscillation, it creates an oscillating electric dipole. It perfectly simulates that single accelerating charge our equation was talking about earlier.
Now, here's where the math we just talked about gets proven in physical space. Imagine we place a detector on a sphere all the way around that generator. When the detector is at point 1, directly parallel to the generator at the equator, we get this massive signal. The electric field is shaking our detector perfectly. But then, look at point 3, up at the pole. The signal there drops completely to zero. No signal at all. Why does it just vanish?
Well, it's all because of what's called the projection effect. At the equator, point 1, the charge is accelerating perpendicularly, side to side relative to our line of sight. And the result? Maximum signal. But at the pole, point 3, the charge is accelerating directly toward and away from the detector. So from that specific perspective, there is no side-to-side wiggling at all. Result? Zero signal. This just brilliantly illustrates that electromagnetic radiation absolutely requires the acceleration of the charge to be perpendicular to your line of sight.
All right, Section 4, Interference and Vector Addition.
Check out this setup showing two sources, S1 and S2, placed side by side. If they both pump electrons up and down perfectly in sync, perfectly in phase, their electric fields add up to create a signal twice as strong at point 1. But here's the wild part, the real trick. If we delay the timing of source 2 so they're exactly 180 degrees out of phase, their fields will be pointing in completely opposite directions at any given millisecond. And this brilliantly shows that the two fields will cancel each other out to exactly zero. So you can literally have two incredibly powerful sources moving furiously, but if they're perfectly out of phase, they produce absolute silence.
We can actually physically prove that this signal delay is entirely based on the distance light travels. Let me walk you through how we do this physically. Step 1. Keep both sources oscillating perfectly in phase. Step 2. Physically move the detector closer to source 2, say to point 2 on our setup. Step 3. Find the exact distance difference, which we call delta, where the time it takes the signal to arrive from S1 is delayed by precisely half an oscillation. Compared to S2, because of that physical travel delay, the signals arrive out of phase at the detector, and boom, you've found the exact spot where the net signal is zero all over again.
And we can take this even further to show that these fields act exactly like vectors. If we take source 1 and turn it 90 degrees so it's horizontal, while source 2 stays vertical and we keep them in phase, well, now at point 1, the horizontal and vertical fields add together perfectly as vectors. If you rotate your detector, you won't find the maximum signal purely vertically or purely horizontally. Nope, you'll find it right in the middle, exactly at a 45-degree angle, which is our vector r here. And if you turn the detector 90 degrees away from that max signal, you get 0. The classical math just works so perfectly in physical space.
And finally, Section 5, the unsolved mystery.
So this complete expression of classical electrodynamics was an absolute triumph of physics, right? But it actually had a dark secret. See, to calculate a field, as we've been doing, you divide by the distance between the source charge and the point you're measuring. But what if you want to calculate how a charge acts on itself? Think about it. The distance from a charge to itself is exactly 0. So how on earth do you divide by 0 in the equation without the math just completely breaking down? This mind-bending puzzle of self-interaction wasn't fully solved back then, and honestly, in many ways, it still haunts classical physics today. It's a brilliant reminder that in physics, every answered question just opens the door to an even deeper mystery. I really hope you've enjoyed this explainer and that it leaves you hungry to explore even more.
Okay, let's dive into this. Welcome to the explainer. Today, we're unpacking a really fundamental property of light that often gets totally overlooked if we just think of it as a simple ray tracing a line across a room. We're going to explore the physics of polarization, drawing directly from Chapter 33 of the legendary Feynman Lectures on Physics. Our main goal today is to truly understand light as a physical, vibrating electric vector that actually interacts mechanically with the materials around us. Here's our roadmap for today. We'll start with the geometry of light, then move to superposition and phase, birefringence and polarizers, Brewster's angle, optical activity, and finally, light's angular momentum.
Section 1. The geometry of light. Understanding the electric vector.
To really grasp polarization, we kind of have to stop thinking of light as just this simple forward-moving beam. As it travels, its electric field is actually oscillating in a very specific plane, perfectly perpendicular to the direction it's moving. And this brings us to a foundational concept, linear polarization. This is simply light where the electric field oscillates back and forth on a single straight line. So if you can picture that invisible straight line just vibrating continuously in space, well, you're perfectly primed to see how the more complex geometries of light are built directly from it. Now, what's really interesting about this slide is how we can break that vibration down physically. Any linear oscillation can be thought of as a mathematical combination, a superposition, of an x vibration and a y vibration. When the x and y components hit their maximums and minimums at the exact same time, meaning they're perfectly in phase, they combine to create a brand new straight line vibration at a specific angle. Moving right along to Section 2, superposition and phase differences. This is what happens when vectors go out of sync. So, we know what happens when things perfectly align, right? But what physically happens when the x and y vibrations don't reach their peaks at the exact same time? Well, when they're in phase, we get that straight line of linear polarization. But when they're out of phase, we get elliptical or even circular polarization. Feynman actually gives us a really brilliant physical analogy here. Imagine you're hanging a ball from a long string. If you pull it back and let it go straight, it swings in a line, right? That's our in-phase linear polarization. But if you give it a little sideways push right as you release it, giving the x and y motions different initial velocities, that ball is going to swing in a sweeping ellipse. And our electric field vectors? They do the exact same thing when their phases shift out of sync. Think about these combinations for a second. We've got x and y vibrations with equal amplitudes but varying relative phases. In the first scenario, they're perfectly in phase, making a straight line. But as that phase starts to shift, you can see the straight line opening up into an ellipse. Keep shifting it until they are exactly 90 degrees out of phase, and boom, you get a perfect circle. The electric vector is literally rotating in space as the beam of light moves forward. How cool is that? Section 3, birefringence and polarizers, filtering the vectors. Okay, let's see how these vibrating vectors actually interact with materials made of long fibrous molecules. This brings us to a classic experiment that demonstrates a phenomenon called birefringence, and we're going to use common cellophane. Here's the sequence. First, unpolarized light enters a sheet of Polaroid, filtering it so the beam becomes perfectly linearly polarized. Next, this polarized light passes through the cellophane. Finally, it meets a second Polaroid sheet. Because cellophane is made of long aligned molecules, light vibrating parallel to those molecules travels at a totally different speed than light vibrating perpendicular to them. This speed difference actively changes the phase of our x and y components as the light travels right through the material. You can see the mechanics of this beautifully mapped out. Those dotted lines, they represent the electric vectors.
Now, if the two Polaroids are crossed at perfect right angles, normally absolutely no light gets through. It's totally blocked. But when you insert the cellophane between them, its birefringence alters the phase between the perpendicular components of the light. This effectively twists the polarization of the beam, miraculously allowing light to pass right through that second crossed Polaroid. The physical structure of the cellophane is literally actively manipulating the light's electric vector.
Section 4. Reflection at Brewster's angle. Polarization by bouncing.
Let's shift gears from light transmitting through crystals to something you probably see every single day. Light bouncing off a flat reflective surface, like a piece of glass or a lake. Have you ever used polarized sunglasses to cut through the harsh glare off the water or a car windshield? I mean, it works like magic, because reflected light is often partially or even fully polarized. But why is that? Why does the simple act of bouncing off a surface actually force light to vibrate in one specific direction? Well, the answer lies in the actual mechanics of reflection. The source of reflected light isn't just a simple bounce. The incoming or incident beam actually drives the electrons inside the glass to oscillate. These oscillating charges then re-radiate the light back out. But here's the catch, and this is absolutely crucial. An oscillating charge physically cannot radiate energy in the direction of its own motion. So at a very specific angle, known as Brewster's angle, the reflected beam and the refracted beam inside the glass form a perfect 90-degree angle. When this happens, any oscillation in the plane of incidence is pointing exactly along the line of reflection, meaning it simply cannot radiate. As a result, the only light that survives the bounce is polarized perfectly perpendicular to the plane of incidence. To understand the quantitative side of this, Feynman models the electric field vectors for different polarization planes relative to the glass. In one scenario, the light is polarized perpendicular to the page. In another, it's polarized right in the plane of the page. By meticulously tracking the amplitudes of the incident, reflected, and refracted waves, and, of course, making sure the total energy perfectly balances out, we can calculate exactly how much light reflects at any given angle. And this brilliantly illustrates the result of those calculations, Fresnel's reflection formulas. Now, without getting bogged down in the real-time algebra here, what you really need to take away from this is that the exact intensity of the reflected light depends entirely on its polarization state and the angles of incidence and refraction. Notice that tangent function for parallel polarization? When angle I plus angle R equals exactly 90 degrees, that denominator approaches infinity, which makes the reflection coefficient drop precisely to 0. That right there is the absolute mathematical proof of Brewster's angle.
Section 5. Optical activity and molecules. The corkscrew effect.
All right, let's move away from flat reflecting surfaces and dive straight into the weird 3D microscopic world of asymmetric molecules. Think of the sugars found in common corn syrup. Some molecules just don't have mirror symmetry. They're shaped literally like spirals or corkscrews. When a linearly polarized beam hits a molecule shaped like a spiral, the electric field doesn't just push the electrons in a simple straight line. Because the electrons are constrained by the actual physical shape of the molecule itself, they're forced to travel up and around that molecular corkscrew. Here's the step-by-step breakdown of what happens next. As electrons are forced along that spiral path, their motion generates a small secondary current perfectly perpendicular to the incoming light. And because the spiral takes up physical space, there is a tiny spatial delay as the current moves from one side of the molecule to the other. This delay creates a phase difference. When these newly radiated fields combine with the original wave, they don't perfectly cancel out. The net result? The entire plane of polarization actively rotates as the light travels through the syrup. The physical 3D shape of the molecule is literally twisting the light.
Finally, Section 6. Light's angular momentum, the grand finale.
We are building up to the most profound physical consequence of this entire explainer, the tangible mechanics of circular polarization. First, let's look at a totally mind-bending concept. Notice how two oppositely rotating vectors of equal amplitude add together perfectly to produce a single vector oscillating in a straight line. Think about what that means. It means that any linear polarization is actually just a superposition of equal amounts of right-handed and left-handed circularly polarized light. You can literally build straight lines out of opposing circles. It's like a giant puzzle. Let's move to and see how this builds into an actual physical force. If we isolate just one of those circular polarizations, we have an electric field that is constantly rotating as it moves forward.
When this rotating field encounters an atom, it grabs onto the electron and forces it to move in a physical circle, perfectly in sync with the rotating electric vector. The light is applying a real mechanical push to the matter. So, the crucial point is captured beautifully in this quote directly from Feynman. A beam of right circularly polarized light carries an angular momentum. For when this beam is absorbed, that angular momentum is delivered to the absorber. Think about that for a second. When circularly polarized light hits an object and gets absorbed, it actually exerts a physical twist on that object. It literally tries to spin it. No way, right? But it's true. To summarize our journey today, we started by looking at light as this abstract, mathematical electric vector, plotting out x and y phase graphs. But we've ended up here, realizing that light is not just a picture or a passive beam of illumination. It is an active, physical force that twists, pushes, and physically rotates the matter it touches at a microscopic level. Which leaves us with an absolutely fascinating thought to ponder. If a simple, invisible beam of light has the mechanical power to exert physical torque on the atoms that make up our world, what other invisible forces are actively shaping the macroscopic reality we experience every single day? Thank you so much for joining me on this deep dive into the physics of polarization. Keep questioning, keep visualizing the mechanics behind the math, and I'll see you in the next explainer. Welcome back to the Explainer, everyone. I'm honestly so excited to get into this one today. We're going to be diving deep into Chapter 34 of our physics journey, visually demystifying some truly mind-bending stuff. We're looking at what actually happens to electric and magnetic fields when their sources aren't just, drifting along, but are moving fast, like near the speed of light fast. By the end of this, I promise you'll look at light, radiation, and even the stars in the night sky in a totally different way. Okay. Really quickly, here is our roadmap for today. First, we'll talk about the speed of information. Then we'll visualize apparent motion, and after that, check out the sheer power of synchrotron radiation. Then we hit the relativistic Doppler effect, the aberration of starlight, and we'll wrap the whole thing up with a massive paradigm shift regarding the momentum of light. Let's get into it. Section 1. The speed of information. This is absolutely foundational for everything else we're going to talk about. So here's the thing. There is a fundamental built-in delay in the universe. Look at the true position of a moving charge. Right now, at time t, it's up there on the top right. But if we're the observers sitting way off at point P, we don't actually see the charge at t. The information about that charge's electric field takes time to travel to us at the speed of light. So the field we're feeling right now, it actually depends on where the charge was in the past, its retarded position down there at point A. Sounds simple enough, right? But when things start moving fast, this little delay changes literally everything. And when we really look at the mathematical reality of this retarded position, the crucial takeaway is that once you strip away all the complex math, only the transverse changes matter. Basically, the side-to-side motions in the x and y coordinates at that past retarded time, that's what actually determines the electric field we measure. Whatever the charge is doing along our direct line of sight doesn't matter nearly as much as that transverse wiggling. That wiggling is what generates the radiation we actually see. All right, moving on to Chapter 2, Visualizing Apparent Motion. How do we actually picture this geometric puzzle? So how do we find this apparent motion? Well, the brilliant trick here is to take the actual messy path of the charge, you can see that loop on the left, and imagine literally sweeping it away from the observer at the exact speed of light. By translating that curve backwards in time, proportional to how long the light takes to reach us, we kind of stretch it out. And that stretched out curve on the right, that is what the observer actually perceives over time, and it's the acceleration of that apparent curve that creates the electric field. Let's look at an extreme example, because this is super cool. If a fast particle is moving in a circle, like an electron zipping around in an accelerator, and we look at it edge on, we don't just see a nice smooth sine wave. Because we have to sweep its motion away at the speed of light, mathematically, it ends up looking like a wheel rolling backwards. You get this resulting apparent motion called a Curtate cycloid shape right here. Take a look at those incredibly sharp points, those cusps, at the very top. And I really want to emphasize this quote from the source text. If it went at exactly the speed of light, they would be actual cusps, infinitely sharp. The physical meaning of that is just huge. A mathematically sharp point on this graph means an absolutely enormous change in acceleration over a tiny, tiny fraction of a second. So instead of a smooth, gentle wave of light, this particle is firing off a massive, incredibly sharp pulse of electric field right at us. Which brings us to Section 3, Synchrotron Radiation. Let's see how this microscopic geometry creates some of the most awe-inspiring phenomena in the cosmos. Okay, so when a uniform magnetic field interacts with a charged particle, it forces it to move in a circle. The magnetic force acts at right angles to the particle's velocity. This means the magnetic field isn't actually speeding the particle up or slowing it down. It's purely changing its direction. And when you get electrons moving near the speed of light in circles like this, whether that's inside a massive lab machine or way out in deep space, they produce those super sharp pulses of radiation we were just talking about. 8 million. Let that number sink in for a second. This represents the mind-blowing energy compression factor for a highly relativistic electron in a synchrotron. Because the electron is practically chasing its own light pulses at nearly the speed of light, the timescale of the emitted radiation gets totally squashed. It's reduced by a factor of 8 million. Actually, twice over near the cusp. So a particle you'd normally expect to emit these long, 20-meter radio waves, it ends up emitting light shifted all the way into the visible spectrum, or even into sharp, highly energetic X-rays. It's wild. Now, if you contrast these sharp, relativistic pulses on the left with the smooth, classical waves on the right, you'll see that passing those sharp pulses through a grating actually gives you a continuous spectrum of visible light. And the crazy thing is, this happens out in nature. Back in the year 1054, Chinese and Japanese astronomers recorded this massive exploding star, a supernova. Surprisingly, European monks completely missed it. But today, the leftover remnants of that explosion make up the Crab Nebula, and it glows incredibly brightly with a continuous, polarized light. That glow is powered by this exact phenomenon: highly energetic electrons spiraling around in magnetic fields, firing off these sharp, relativistic pulses of synchrotron radiation. Okay, Chapter 4, the relativistic Doppler effect. Now we're bringing the observer's own perspective directly into the mix. So I want you to ask yourself, what exactly happens to the light waves if the source isn't just moving in a circle, but is hurtling directly towards us as it emits the light? Well, if the source is moving toward us, it literally chases the light waves it just emitted. The physical motion means the waves actually get squashed together from our perspective. The physical distance between the peaks is shortened. And shorter waves mean a higher frequency. So light from an object moving toward us appears shifted toward the blue, higher frequency end of the spectrum. Now, because this is all happening at relativistic speeds, we also have to factor in time dilation, which, makes the exact mathematical formula a bit more of a headache, but the physical squashing effect, that's exactly what's going on here. All right, Chapter 5 introduces another fascinating real-world consequence of motion and wave geometry, the aberration of starlight. Remember, light propagates in 3 dimensions. The wave isn't just moving along a single neat little axis, it's moving obliquely. To represent this mathematically, physicists use a 3D wave vector that points in the direction of travel. And because we measure the phase of the wave as it crosses our own coordinates, our perception of the wave actually changes depending on our angle and our own motion relative to it. Think about it like this. Imagine a star positioned directly overhead, sending light straight down at the speed of light. If we are standing on Earth moving sideways through space, we can't just point our telescope straight up. Because we're moving laterally while the light travels down the tube of the telescope, the light would just hit the inside wall of the tube. To actually catch the light all the way down to the eyepiece, we have to tilt the telescope slightly forward, right into the direction we are moving. If the relativistic math ever starts feeling a bit too abstract, just remember this everyday analogy. Tilting a telescope is exactly like tilting your umbrella forward when you're walking quickly through rain that's falling straight down. The faster you walk, the more you have to tilt the umbrella to keep from getting wet, right? Well, the faster the Earth moves in its orbit, the more astronomers have to tilt their telescopes to see a star. This aberration is literally definitive, measurable proof that the Earth is moving. And that brings us to our final section, Chapter 6, the momentum of light. This is where everything culminates in a major paradigm shift about what light actually is. Up until now, we've mostly been ignoring the magnetic field inside a light wave. But when a light wave hits an electron, the wave's electric field drives the electron up and down. And remember, the light wave also has a magnetic field acting at right angles to that electric field. Since a magnetic field exerts a force on a moving charge, as the electric field moves the electron up and down, the magnetic field is simultaneously pushing it. If you calculate the cross product of that up and down velocity and the magnetic field, the resulting force always points perfectly in the direction the light is traveling. Light is literally pushing on the matter it hits, We call this radiation pressure. So, in the classical view, light is this continuous electromagnetic wave that exerts a physical push, radiation pressure, through the combined action of those electric and magnetic fields. But here's the kicker. This seamlessly matches up with the quantum view. In quantum mechanics, a beam of light is treated as a stream of discrete particles, called photons. And just as the classical wave exerts a continuous push, these quantum photons carry real physical momentum. It's almost like a stream of tiny, spinning rifle bullets hitting a target.
Which leaves us with a pretty profound question. If light acts precisely as both a continuous geometric wave that squashes and stretches with motion, and simultaneously acts as a stream of momentum-carrying bullets that physically push matter, what is its true nature? This beautifully structured wave-particle duality is exactly where classical physics ends, and the wild, fascinating world of quantum behavior begins. I really hope this breakdown of Chapter 34 helped illuminate the mechanics of our moving universe for you. Stay curious, keep learning, and I will catch you in the next explainer.
Welcome to the Explainer. So today we are diving into the totally mind-bending reality of quantum mechanics. We're unpacking Chapter 38 of the Feynman lectures, which basically proves that our comfortable classical ideas of pure particles and pure waves, they completely fail when we zoom in close enough. We literally have to learn a whole new way to view reality. But before we get lost in the theoretical weeds, I want to pose a profound, everyday question to you. Why doesn't the matter that makes up your body just collapse in on itself? I mean, classically speaking, an electron orbiting a nucleus should constantly radiate light, lose its energy, and just spiral right into the center, completely destroying all matter. Obviously, that doesn't happen. Well, by the end of this explainer, you're going to understand the exact physical reason why matter actually has volume. Here's our roadmap for today. First, the wave-particle paradox, then the uncertainty principle, followed by the diffraction of particles, the size of atoms, quantum energy levels, and we'll wrap up with the quantum philosophy. All right, let's jump right into Section 1, the wave-particle paradox. So, you know the classical idea of a particle, right? A tiny, hard dot with an exact location and speed. Well, it turns out that's fundamentally flawed. In quantum mechanics, we actually describe events using something called a probability wave amplitude. Now, this is a complex number, and if you take its absolute square, you get the probability of finding a particle at a specific place in time. What this really means is that a particle isn't a solid dot at all. It actually behaves more like a localized wave of chance. And this image right here brilliantly illustrates the problem with trying to pin down a particle. Just imagine a finite wave packet with a length we'll call delta x. This is basically the region where we might actually find the particle. But there's a basic property of any wave you got to remember. A finite short wave train cannot have a unique, perfectly defined wavelength. And since quantum mechanics links a particle's wavelength directly to its momentum, an indefinite wavelength means a fundamental indefiniteness in momentum. You literally cannot perfectly know both at the same time.
Moving on to Section 2, the uncertainty principle.
Let's actually see how this wave nature naturally creates uncertainty in our physical measurements. Imagine we have particles flying in horizontally toward a narrow slit of width b. By forcing the particles through this slit, we're measuring their vertical position quite precisely. But look at what happens on the other side. The particles spread out. Just like light diffracting, the wave nature of the particles causes them to fan out. So by pinning down their vertical position, we accidentally cause their vertical momentum to diffuse completely unpredictably. And we can look at this from the other direction too. Suppose we want to measure a particle's momentum extremely accurately using a diffraction grating. To get a really sharp, precise measurement of momentum, the particle's wave train has to physically interact with the entire grating all at once. That means the wave train must be very long. But, as we saw just a minute ago, a long wave train means the particle's position is highly spread out and totally uncertain.
So here's the absolute crucial point. The uncertainty principle restricts predictability. A really common trap is to say, well, I saw it hit the screen right here, so I know its position now, and I can just calculate the exact momentum it must have had to get here. And sure, you can do the math after the fact, but quantum mechanics limits our ability to predict the future state of a system. Once that particle went through the slit, its future momentum became fundamentally unpredictable.
All right, Section 3, diffraction of particles. So what exactly happens when we take these abstract wave concepts and bounce them off solid physical objects? Well, imagine parallel crystal planes separated by a specific distance. If you shoot particle waves, like electrons or neutrons, at a crystal, they reflect.
But here's the catch. They only produce a strong, coherent reflection if the extra distance traveled by the deeper wave equals a whole integral number of wavelengths. Otherwise, the wave crests and troughs just cancel each other out.
This actually has massive real-world implications. Imagine taking a bunch of neutrons, which we know are absolutely particles, and letting them diffuse into a really long block of graphite. Because of their wave nature, they just bounce around inside by diffracting off the carbon crystal planes.
But look at what happens to the intensity. If the wavelength of a neutron is more than twice the distance between those crystal planes, it actually can't diffract. It just sails straight through. And because wavelength is inversely related to momentum, only the absolute slowest neutrons with the longest wavelengths bypass the scattering planes and manage to emerge out the far end. I mean, it is just an incredible visual proof that physical particles behave exactly like waves.
Which brings us to section 4, the size of atoms.
Okay, it's time to finally answer our opening question. Why doesn't the atom just collapse? Classically, like we said, the electron is doomed to spiral in. But quantum mechanically, as the electron gets pulled closer to the nucleus, its location becomes more precisely defined in a smaller and smaller space. And according to the uncertainty principle, shrinking that position spread forces the momentum spread to absolutely blow up. Higher momentum means higher kinetic energy. So, as the nucleus tries to compress the electron literally fights back with massive kinetic jiggling. The atom eventually settles at a compromised distance, known as the Bohr radius, which perfectly minimizes the total energy. That quantum resistance to compression is exactly why tables are solid and why matter has volume. And if you plug that compromised distance back into the energy equation, you get exactly negative 13.6 electron volts. Now, this isn't just some fun math trick. This is the exact, real-world measured ionization energy of hydrogen. It's amazing because it beautifully anchors our theoretical quantum physics into hard, proven reality.
Next up, section 5, quantum energy levels.
So what happens when these confined wave electrons gain extra energy? Well, think of the allowed bound energies as distinct horizontal levels, say labeled E0, E1, E2, and so on. It's kind of like sound waves confined in an organ pipe. They can only vibrate at specific resonant frequencies. In the same way, an electron bound in an atom can only vibrate with specific, allowed energies. It simply cannot exist anywhere in between these levels. And here is where it gets truly magical. When an atom drops from a higher energy state to a lower one, it emits light. The frequency, or the color, of that light directly corresponds to the energy difference. If an atom drops from state 3 to state 1, it emits a very specific frequency. If it drops from 1 to 0, it emits another. And because energy is always conserved, the sum of those two frequencies will perfectly equal the frequency of a single direct drop all the way from state 3 down to state 0. This is known as the Ritz combination principle, and it literally maps out the distinct colors of light that every single element in the universe emits.
Finally, we arrive at section 6, the quantum philosophy.
It's time to zoom out a bit and look at how these quantum realities completely reshape our fundamental philosophy of the universe. In quantum mechanics, making an observation is never, ever passive. When we look for a phenomenon, we cannot help but disturb it in a certain minimum way. Measuring an exact position permanently and necessarily destroys the predictability of its momentum. And it's not a flaw in our instruments. It is a fundamental feature of reality that's required for nature to be logically consistent. But hey, before we totally throw classical physics under the bus, consider this wonderful quote from Richard Feynman. He points out that even in a classical, deterministic world, things get unpredictable incredibly fast. Think about water splashing over a dam. It seems totally random, right? That's because tiny, microscopic irregularities in the water are vastly magnified as it falls. So chaos reigns in classical physics too, purely from a practical limitation of precision. So I want to leave you with this provocative thought. Can we ever truly predict the future, or is the universe just inherently designed to keep us guessing? Whether it's the chaotic splashing of a classical waterfall or the fundamental, inescapable uncertainty of a quantum wave, nature seems to fiercely protect its secrets. The next time you knock on a solid wooden table, just remember that its very existence relies on a universe that outright refuses to be pinned down. Thanks so much for joining me on this explainer, and I'll catch you next time.